Bom dia a todos. Good morning. Good. Obrigada. Good morning, everyone. Welcome to the first HOPTEC Symposium. We're going to start briefly. Just waiting for my co-host.
Apresentação?
Sim, não está?
Não está. Não está a morrer. Não está?
Já está. Okay, now we're on. Good morning, everyone. Thank you all for coming. We know for the students mainly and also the professors, you are in the middle of a lot of evaluations. So thanks for being here. My name is Inês Godet. I was a biological engineering student here at Técnico back in the day, you know. I graduated in 2015. And I was a student. I was lucky enough to go to Hopkins, to the lab of Dr. Danny Wirtz, who's sitting here in front, to do my master's research. Back then, I used the spheroid model to study hypoxia in breast cancer cell lines. That really opened my appetite for the academic path. So then I was also lucky enough to stay at Hopkins for my PhD, where I continued to explore hypoxia and breast cancer, but with a lot more tools. Eventually, I graduated from Hopkins, and now I'm doing my postdoctoral training at Memorial Sloan Kettering Cancer Center. It's a really long name, but it's basically a very good cancer center in New York. And I continue to study metastases, now in lung cancer. And my goal is to use biological or bioengineering tools to solve small questions in the big world of metastases that other cancer biologists can't really see because I believe they don't have the tools. And now I'm going to let my colleague speak.
Hello, my name is Andre. I'm a PhD student at Johns Hopkins, also in Danny Wirtz lab. I was a former alum of Técnico in the Department of Electrical and Computer Engineering. And now I study cancer invasion and metastasis in 3D.
Okay, so just to give you a very brief overview of our program, you already know that is a partnership between Hopkins and Técnico, hence the name HOPTEC. And this is a partnership with many years. We're going to tell you a little bit of that story today. It started back in 2014 with a student who is also sitting here in front, Leonor Guedes de Silva, also a biological engineering student. And then since then, many students had the chance to go do their master's thesis research at Hopkins. And eventually, Andrea and I, who got that chance, started thinking of making this a more official program. So we spent some years talking about it, and then some years working on it, and then we finally got it. And I don't need to introduce Técnico to you, but as you know, it's the best school of engineering in the world. Just kidding. It's one of the best. And obviously, it's very well ranked in Europe and in the world again, and it puts our University of Lisbon up there thanks to all the publications we do and the breakthroughs we do. Sorry, maybe I should just use this. For those who don't know where Johns Hopkins is exactly, we can tell you it's actually not that far. If you just look in front, it's right there. It's only 5,000 kilometers away on a straight line. And now Andrea is going to tell you a bit more about Baltimore.
So, in case you don't know your geography, Baltimore is located between Philadelphia and DC. It is situated in the east coast of the US, and it's specifically at this location because it's such a a strategic location for between other Ivy League schools. And some people call it the Charm City. I'm extremely biased, but I also think it's extremely charming. This is a drone video of Hopkins, the campus. It was the first, for those who don't know about Hopkins, it was the first research university in the US, and is regarded as one of the top medical schools in the United States, and leading also in the biomedical research field. And for the last 44 years, it has been the top nation, it has topped the nation in federal research funding with over $3.4 billion that they just spent in 2022 alone. So that's almost the entire budget of Portugal. So this funding drives really groundbreaking advancements. Some of them, if you know the Hubble and the James Webb Telescope, they were built and controlled from Hopkins, and they lead other research fields such as immunotherapy, vaccine technology. And so this program, HOPTEC, is really important because it bridges these two amazing institutions, Técnicos, engineers, its excellence, and also Hopkins' leadership in medicine, and really make this collaborative platform for the next generation of researchers and also future leaders in the field.
Yeah, so we signed the Memorandum of Understanding last year, actually around this time, and that was actually the official start of this program. And even though you'll see a lot of our initiatives, but even though we already have a lot ongoing, we want to continue to expand this program. So if any of you has any suggestion, comments, feel free to come to me or Andre throughout the day, and we can discuss. Also, a big acknowledgement to FLAD, the Foundation for Development between Portugal and the US, because without their funding, we would not be able to kick off the program last year. So that was critical, and that was with a huge help of Denise as head of the international affairs here at Técnico.
So behind this program, there's a huge team involved. We have Professor Danny Wertz, Professor Cláudia Lobato da Silva, Professor Jude Philip, Tiago Fernandes, and Inês Godet and I as part of the scientific board. So any project involved with the HOPTEC is evaluated by this scientific board. We also have an amazing support team, Margarida Rodrigues, Vasco, Maria José Ferrão, and Denise Matos, who really help moving forward this project.
Yeah, and now a little bit about the initiatives, like I promised. So you are today participating in our first symposium. We hope we can do this annually. And hopefully our plan is next year it will happen at Hopkins, and we will try to have enough funding to sponsor students from Técnico to attend. Today, just a brief overview, we try to bring you some applications of engineering in health, because that's currently our main focus given our personal experiences and interests. But again, we plan to expand, okay? So we can talk about it. We will also have two presentations from our HOPTEC scholars from 2024, who are here sitting in front, and who did an amazing job presenting their dissertation a couple weeks ago. And in the end of the day, or at the end of the session, we'll have a discussion panel where we'll all, hopefully, feel free to contribute. Try to talk about next steps, where can we go from here, what have we learned, and what ideas do you all have? Oh, and then we'll have the poster awards, which is very important. So whoever is presenting posters, best of luck. For everyone else, stay around over lunchtime. You can go check the posters and ask questions. And then at the end of the day, also big announcement for the new 2025 HOPTEC scholars.
So on top of another initiative from HOPTEC is the webinar series. Every single month, we have talks from faculty from both institutions that present their cutting-edge research. It's an amazing opportunity for trainees to learn from their research and also to interact with faculty from both institutions. It's also a great opportunity for to start new collaborations. So we highly advise, if you don't know about this initiative, to also stay tuned. These are some of the speakers we had over the last few months, and they go from a different spectrum of talks and fields. So we have immunotherapy, 3D imaging, cell metastasis, cancer cell metastasis. So if you're interested in learning more about these talks, they are also available online on YouTube, so you can see previous research talks from these faculty.
And yet another initiative. We launched actually the grand competition. This is a very symbolic amount of money, 1,000 euros. But the goal is to really connect one student or trainee from Técnico with one from Hopkins. They write a small proposal, just to exchange a technique or an analysis method, It can start small, but our goal is to really start the conversation there and then further expand the collaboration. Eventually the student can go to Hopkins and do some things themselves. So that was the idea. So later today, we're also going to announce the winner of this competition. Or the winners, I should say, because it's one student from Hopkins and one student from Técnico.
Okay, so the main initiative of HOPTEC is allowing students from Técnico to do their master's thesis abroad at Johns Hopkins. So this is the HOPTEC Scholars Initiative, and it provides transportation and a stipend for students to spend a full semester abroad. The HOPTEC Scholars awardees of 2024, they were Inês Reis and Alfredo. They are sitting here, and you'll be learning more about their research. They will present a short lightning talk about their master's thesis work. And this is some of their, photos on the last few days at Hopkins. And yes.
Yeah, and we're going to jump right away to these research talks. But before that, we would like to take a tiny break just to do some appreciation. First of all, we would love to call Denise Matos to the stage. And Professor Wirtz, please. Yeah, so it's missing a signature, but we'll fix that. You can come to the stage. So we just want to acknowledge Denise's role in launching the HOPTEC program officially. It was a lot of work, a lot of hours, a lot of meetings, and she went way and beyond. She presented our program at FLAD. She vouched for us to Técnico, to all the leadership here, so she's amazing. She's no longer at Técnico, but we could not done this without her. So this is just a little appreciation certificate. Thank you.
Thank you so much, Inês, André, and everybody that participated in this great project. It was all my pleasure. It was not too many work, too many hours, and too many meetings, because every meeting was a pleasure to work with you. You are the great one. The Técnico alumni do an excellent job all over the world, and it's my pleasure. While I was here working at the International Affairs area, and it's still my pleasure while I'm now representing at the national level the internationalization. So please give an applause to them, because they are the one that did everything, and it's great what you did.
Thank you.
And thank you, Professor.
Very cool.
Okay, our next acknowledgement is to Margarida Rodrigues. Do you want to come to the stage, Margarida? Yes. Yay!
This was not on the schedule, so they were not prepared.
Can you, desculpa. So Margarida took over since Denise left Técnico, so she's been our manager on site. So the implementation of this program really grew over the year of 2024. all the seminars, all the competitions, this gigantic event that you're attending today, it was all Margarida. So thank you so much. And do you want to say some words?
Well, first of all, thank you for this surprise. This was actually not initially in the schedule. They just surprised me with this idea of certificate. So thank you for this, and it has been a pleasure. It has been very interesting to see this project, this program growing, and I hope it continues to grow even more because it really has a lot of potential. So thank you.
Okay, we're going to be super quick now because Maria José does not want to come to the stage, so we just want to say that we're very grateful for all her help. She works with the students directly to help them book their trips, get their refunds, and she also contributed a lot to the organization of this symposium today, all the logistical details, so thank you so much. We can clap for her. And now, a very important recognition is due. So, Professor Wertz, if you could. We're going to call Leonor Guedes de Silva, or Dr. Leonor, I should say. She was the first student back in 2014 to have a casual conversation with Professor Wertz, and it started all of this. So she was the first to go to the Wertz lab to do her master's thesis, and then I showed interest. She was kind enough to put me in touch, and from there, many students have gone. So big, big, big clap for her. Literally, we could not all be here today if it wasn't for you. So.
And all of you, but yes.
we were reminiscing of that auspicious moment where I just re-entered this building from the main door and was making sure that I remembered the story correctly, where your desk was on the left and you were giving tours that summer to random visitors like me, and then we hit it off, and the rest is history. It was such a amazing, and it takes special people like you with a sense of initiative, of risk takers too, right? You were taking a risk. Maybe you didn't know what Baltimore was or what Hopkins was, and it's Johns Hopkins. There's an S there to confuse everybody. But thank you for taking that chance on us, and you triggered all this now, what has become a real pipeline, actually. So there's a little recognition for you.
Thank you, Denis. No, exactly. I guess it's the little trigger. But Denis, I think it takes two to dance the tango, huh? And I think if it wasn't for your openness to also, invest on the Portuguese community of scientists and entrepreneurs, then my email would have never gotten an answer, and things wouldn't have gotten arranged, and there you go. And I'm really happy that this is happening here because at the time was figuring out everything from scratch, and support was not as good as this program is offering. So you can count always with my support to make sure this is a success.
Okay. Typical Portuguese humility and excellence both at the same time. And so you've heard it from Denise, it's not me, it's someone else who did it. You just heard from Lenore, it's not me, it's someone else. So I guess I want to say I'm a sucker for this, where the students, 6 months into it in Nation at Fredo both, right, they still pinch themselves being at Hopkins. There's something to say about recognizing the chance and grabbing it at both hands and running with it. But I have to recognize that, of course, I'm married to a Portuguese, so that starts with that. So I come here twice a year, so I had to organize something. But at the same time, more importantly, incredibly well trained, and just simply a good heart, a good sense of the special, I guess, privilege to some extent, but at the same time created by your own initiative, by your own. You create your luck, right? And it's true. So I wanted to recognize this. I've seen it again and again in action, and I'm just a complete fanatic of that. Just amazing, this excellence and humility at the same time. This is fantastic.
Thank you.
So, as you can see, this was not on the schedule, but coming back to the schedule, we have two presenters. These were the ambassadors in 2024. Inês Reis is going to present her thesis researching 3D single-cell mapping of the connectivity between the Alzheimer's brain and eye. And Alfredo is going to tell you about 3D mapping of the serous tubal carcinomas in whole human fallopian tubes. So, without further ado, Inês, the floor is all yours.
Hello everyone, can you hear me? Okay. Can you hear me? Okay. So hello everyone, thank you so much for coming. Welcome to the topic on 3D single cell mapping of the connectivity between the Alzheimer's brain and the eye. I developed this project during 6 months at Johns Hopkins University as part of the HOPTEC program. So let us start. According to the World Health Organization, more than 55 million people worldwide have dementia, with Alzheimer's disease accounting for 60 to 70% of all dementia cases. While the mechanisms underlying Alzheimer's disease aren't completely understood, the extracellular accumulation of A-beta in the form of synapse and the intracellular deposition of tau in the form of neurofibrillary tangles in the brain are proposed to actively influence neuronal loss and progressive cognitive decline. While these pathologies have been widely studied, early diagnosis still remains a challenge. Hence, it is important to investigate potential biomarkers to revolutionize AD treatment. So, in recent years, the eye has gained significant importance in early AD diagnosis. Studies on both humans and transgenic mouse models of the disease have highlighted important anatomical and functional changes in the eye that often precede memory and cognitive impairment. Retinal layers such as the ganglion cell layer and the nerve fiber layer are often affected in AD, exhibiting significant thinning. Moreover, changes in retinal vasculature are also notable with decreased blood flow and loss of vascular integrity. So, given this, we hypothesize that Alzheimer's disease affects the eye of a transgenic mouse model. But how can we possibly assess that? Although current methods have been proposed to assess common pathologies of AD, none has explored the linkage between the AD brain and the eye within a three-dimensional construct. Furthermore, current methods present an inadequate trade-off between the reconstruction of large volumes and the number of structures labeled. So, to address this problem, we implemented CODA, which is a novel methodology designed to reconstruct large tissues at subcellular resolution using serial section of methoxylin and iosine-stained tissues. Our main goal here is to modulate a system capable of providing enhanced interpretation of the intrinsic relationship between the Alzheimer's brain and the eye within a three-dimensional construct. So, before we can apply CODA, we had to choose the appropriate transgenic mouse model. Here, we have the 4 most commonly used mouse models. Although the 5X FAD, which is the second one, is an imperfect model, It presents changes in the brain and the eye that are very similar to the ones that are observed in the human. So the brain and the eye were collected from two samples, a 12-month female 5X FAD mouse model and its age-match control. After sample collection, we proceeded to serial sectioning, and every 2 slices were stained with hematoxylin and eosin, and then they were scanned. Briefly, hematoxylin eosin staining is a combination of 2 stains: hematoxylin, which stains nuclei and has a deep blue-purple color, and eosin, which stains proteins non-specifically and has a pink color. So after scanning, we proceeded to the generation of the deep learning models using manual annotations. And to achieve this, pixels were annotated to represent different tissue types and to create high-quality ground truth annotations for accurate model performances. Afterwards, the images were segmented based on pre-trained deep learning models to create classified images. The model's performance was tested externally using an independent data set. Because of the complexity of the organs, here we created 4 different models to decrease the complexity of the learning task. Here we have our first model, which is the optic nerve model that segments the H&E stained tissues into 3 different labels: the optic nerve, brain, and the eye. The model's performances is evaluated using a confusion matrix that allows a comparison between the ground truth, which are the real class values, and the predicted values. This model reached an overall accuracy of 96.3%. Afterwards, we were interested in evaluating the distribution of plaques in the brain. So we divided the brain in 8 different regions that are known to be affected in Alzheimer's disease. This model reached an accuracy of 94.3%. The last brain model divides the H&E stained images into plaques and non-plaques. This model reached an accuracy of 89.3%. So the final model, for the final model, we were able to extract 29 different structures from the eye. And this model performed extremely well and reached a global accuracy of 91.6%. Here, I'm going to show you a more detailed illustration of the segmentation in 4 different regions of the eye. We have the retina, the lens, the cornea, and the uvea. And these images illustrate the importance of artificial intelligence in taking small annotated H&E images to extract detailed features from a larger data set. So after deep learning segmentation, we proceeded to the 3D reconstruction. So the tissues that were segmented were aligned and consolidated into a 3D matrix. Here we have a video of the optic nerve model where we can clearly see the connectivity between the eye and the brain. We also performed a 3D reconstruction of the different regions of the brain. And finally, the 3D reconstruction of the plaque model was extremely important for us to visualize the astonishingly high number of plaques that are present in the brain. On the right, we have a video of the 3D reconstruction, but also the distribution of plaques throughout the whole brain. So, our final step was to perform quantitative comparisons across the different data sets. But first, for us to obtain important quantitative data, we implemented color deconvolution. Color deconvolution is a method based on a Lambert-Beer law that separates bright field images into 3 channels, the red, green, and blue, and hence can be utilized to obtain single stain images. So, as I previously told you, hematoxylin stains nuclei. So we apply color deconvolution to extract the hematoxylin channel from the H&E images. The algorithm here implemented for cell detection is designed to detect intensity local maxima. So by applying this arithmetic cell algorithm on a generated mosaic for different combinations of the parameters, And by comparing it to a ground truth, where we manually counted the cells in the mosaic, we were able to find the optimal parameters. Afterwards, we applied the algorithm to all of the extracted imetoxylin images. So after we obtained important data, we now proceeded to the results. And here particularly, we will present the number of plaques per brain region. As we expected, plaques were absent throughout the whole mouse brain of the wild type, but they were clearly present in the 5X FAD mouse model. In particular, the highest number of plaques were found in the cerebrum, reaching an astonishingly high number of 250,000 plaques, and reached low levels in the fibria and cerebellum. We were able to count 400,000 different plaques, which is a very, very high number. So afterwards, as articles have reported visual deficits in both humans and transgenic mouse models of the disease, we wanted to explore the number of cells, the volume of the samples. However, due to varying volumes between the samples, we wanted to introduce a more accurate measure. So we decided to use cell density, which represents the number of cells per unit of volume. So we found that the highest cell density was found in the outer nuclear layer, and in the nuclear, which are characterized for a high density of cells. And as we were expecting, the lowest cell density was found in the lens fiber and the capsule, which reflects their transparent and avascular nature. So afterwards, we analyzed the difference in cell density, and we found that there were actually some visible alterations. Specifically, we found that there was a 1.42-fold increase and a 1.2-fold increase in the autophotoreceptor and vasculature, respectively, when comparing the diseased mouse to the age-matched control. This may mean that the plaque pathology influences the cell integrity in the visual system. So finally, this research elucidates the complex spatial relationship between the eye and the brain, establishing a robust framework for quantifying inter-organ dependency. To the extent of our knowledge, this is the first attempt to introduce a learning-based approach for 3D reconstruction of the connectivity between the eye and the brain. We showed changes in cellular density between the 5x5 model and its age-matched control, and distinct distribution pattern of plaques in the brain. Future work should include a larger sample size to evaluate the reproducibility and reliability of findings. Finally, and very quickly, I want to thank everyone who helped me throughout this journey, Donald, André, Vasco, Dr. Denis, Dr. Ashley, and Dr. Peixum, whom without I couldn't possibly do this work, and I want to thank Inês and André for creating this program. Thank you.
Thank you so much. Is this on? No? Okay. Okay, thank you so much. This is really impressive how she was able to do this in just 6 months. And now we'll open the floor for any questions. So if you have any questions. No, we can. No. Okay, I guess I can start to break up the ice. So you mentioned this technique CODA for 3D imaging. I was wondering if you could expand a bit more on what's special about this imaging and why could you not do this with CT scan or MRI or any other 3D imaging techniques available?
Okay, so let me see. So as I was explaining in the beginning, the problem with the current methods for 3D imaging and imaging techniques is that they may have high resolution, but then they have low contrast, or vice versa, and they may be able to reconstruct large volumes, but then we only have very few labels. And what's incredible about CODA is that we can have this trade-off between having high volumes, as you could see, for example, the eye, and have a high number of structures, as you can see, like in the eye as well, because we were able to extract 29 different labels, which is something that, or at least for the eye, I think has never been done before.
Thank you very much, really impressive. I'm not at all an expert in these microcellular techniques, but I have the impression there are tracing techniques that can be used to map connections in the brain in particular, and it sounds like that's what you're also trying to do. Do you know which ones I'm referring to? Which kinds of tracers?
Yeah, I think so.
Do you want to comment on how they relate to your technique and why they are maybe not measuring exactly the same thing, or if they are? Because that's what we would normally use. I work with MRI, and that's what we normally use as our kind of ground truth for the connections we measure with MRI. So I'm wondering why this is not also an interesting technique for you.
Yeah. So if I understood correctly, it's just like why I chose CODA instead of, for example, using... Okay. So first of all, it's just the lab where I worked in. It was the lab where CODA was developed. So that was, of course, my first choice. And then, as I was explaining previously, I think the fact that we are able to reconstruct these 3D volumes and have such a high number of labels, we have like this framework where we can just like use it to then perform an infinite amount of quantifications. And I don't know, but I feel like this is probably cheaper than other methods because hematoxylin and ozone is a very cheap stain to utilize. And also we here, maybe I should explain better, because here when we are staining the sections, we stain one in every 2 sections, so that the intermediate sections can then be utilized for example, spatial transcriptomics. But for us to use that, because it's a very, very expensive technique, we first analyze this and see where changes may happen, and then use those techniques to evaluate. I hope I answered your question. Thank you.
Okay, if we don't have any other questions, then let's give a round of applause for Inês.
Thank you.
A lot of slides. Okay, so now let's welcome the second speaker of today, Alfredo, with the thesis of 3D mapping of serous tubal carcinomas in whole human fallopian tubes. Okay.
Hello, everyone. Can you hear me? Yes, I think so. So I'm very happy to have you all here. Welcome. Thanks to Inês, Andre again, Denis, and everyone involved in this project. It was such a huge opportunity for me, so I'm very happy to show what we've been working this past, while I was there during 6 months. So, of course, the title is 3D mapping of serous tubal intraepithelial carcinoma in whole human fallopian tubes. And I think we have to start with a brief introduction in ovarian cancer. So these are all the statistics for the US, since my work was done there. It represents the 17% of cases of female genital cancer. And for this year, it was predicted that around 20,000 new cases would appear, and sadly, 13,000 people would die just because of this disease. High-grade serous carcinoma is one of the types of ovarian cancer, and its deadliest form accounts for around 70% of the cases and 80% of the deaths. So very interestingly, around 20 years ago, there was a big change in paradigm, and in the paradigm of how we understand this disease. it was discovered that there are these precancerous lesions called serous tubal intraepithelial carcinoma that starts in the fallopian tube and then migrate to the ovaries. So that's very different compared to other types of cancer that are actually usually start in the same organ that they develop. So that brings us to the state-of-the-art technique in which that is used for detecting these lesions. So you have to completely extract the fallopian tube from a patient. Then you slice it every 2 to 3 millimeters, and you will obtain something like this. And then what we do is to, well, if you were doing the state-of-the-art technique, you would take histopathological images from each of these pieces and see with your own eyes, like manually, if you are in the presence of lesions or not. So that, of course, has a lot of limitations. The most important ones is that we are completely ignoring the 3D morphology of the lesions. So since we are cutting every 2 to 3 millimeters, we are missing everything that's going on in between. So first, this is a problem because the lesions are, of course, in 3D. They are not just 2D in an image. And also, we are undersampling. The lesions go from 10 to 100 micrometers long, and that means that we are for sure missing a lot of them. And third, most studies are done in patients that already have cancer or other types of diseases, or they have genetic predispositions. So there's a lot more research that needs to be done with non-disease patients. So I want to talk about more or less the current truths in the literature that come from these studies. So first, it is believed that there's a low incidence of these lesions in the healthy population, around 0.01%. And as a corollary of this, the presence of a lesion would imply a high risk of developing ovarian cancer. Then we have these two that say that most of the lesions should be present in the fimbria, or almost all of them, and also you should only mostly find them in postmenopausal cases. And finally, that there are only main 3 phenotypes. And my job during this presentation is show you that all of these statements are not exactly true according to our new study. So in order to do that, we set this goal to create a pipeline that would allow us to map all of the lesions in healthy human fallopian tubes. For that, we have 4 steps. Let's start with the first, that consists on tissue processing. So tissue processing, we were able to get 5 donors. So we got 5 fallopian tubes that we formally fixed and paraffin embedded. And one of the key differences is right here, in which we completely slide the fallopian tube from end to end. That is very different from what the state-of-the-art that I just showed. And we, of course, apply H&E and HC stains. And we scan these images so we can analyze them in the computer. So the factors to consider if you are in the presence of precancerous lesions is aberrant morphology, p53 positivity as a marker of mutation, and Ki67 positivity as a mark of proliferation. That means you are in the presence of a STIC, serous tubal intraepithelial carcinoma, but there are other types of lesions. So if you have aberrant morphology and mutation markers, but you don't have proliferation, you are in the presence of a STIL, that is a lesser type of lesion. And you have a third one in which you don't have aberrant morphology, but you do have mutation and not Ki67 positivity. That's a p53 signature. So these will be the 3 phenotypes that we're going to base all of our study at the beginning from. So we can continue now to the CODA computational methods. It all starts by registering these images that we scanned, and then we do several tissue annotations, both in H&E and in IHC, to be able to train an AI, a convolutional neural network, to be able to detect the presence of both p53, Ki67, and epithelium. The goal of this is to be able to then use other computational methods to create a pipeline that will semi-automatically detect these lesions. So first, here you can see the results of our models. So you can see in these images that after we apply the models, we can detect in the first image where is the epithelium. That is where the precancerous lesions will develop. and the positive signals from both the mutation markers and the proliferation markers. If we combine these three, as I said before, we're going to be able to identify what type of lesion we are looking for. So we have images for the whole fallopian tube end to end. Then we stack them, and we are able to create 3D volumes that, if we combine, we're going to be able to get the connected components that each of them would represent one lesion. From each of them, we can get several stacks of images, as you see on the far right. And this we manually create, we manually analyze to be able to find if we're in the effective case of a stick, a steel, or a pre-53 signature. So we can finally move on to get some results. With this 3D volume, what we do is to flatten it out to get what we call a C projection, so we can have an overall view of what's going on in each sample. And that's the first thing I'm going to show you. This is the result of a 27-year-old patient. This is the whole fallopian tube. And so this will be the part, the isthmus that is connected to the uterus. Oh, sorry. Then this part in the middle, as you can see, it's full of lesions. And the fimbrial right here that's connected to the ovary just has one. For this case, this patient, 28-year-old, we only found one lesion. That zone is the fimbriated end, close to the ovary. Here we have a 63-year-old in which we have two lesions close to the uterus to the fimbriae. In this case, we have a 60-year-old with several lesions in most of the fallopian tube. And finally, the 72-year-old case that has lesions all over the place. And I want to highlight this remarkable one, that it's a very big lesion that it's one of the worst lesions that we saw. I want to really highlight that this is the first time something like this has done. It's the first time that we can see at single cell resolution where exactly each of the lesions on human fallopian tubes are located. So I think now you will believe me that these are not exactly true. So these were the statements that we had, and it's not exactly true that there's a low incidence. We saw in 5 cases that there were a high presence of lesions. Furthermore, if we plot everything on a heat map, we can see more or less the distribution. This is for the counts for the 5 samples. And we can see that most of the lesions are actually in the ampulla rather than the fimbriated end. So then again, we can see that not all of them are in the fimbria, not most of them. Continuing with that, we can check in this graph the difference between premenopausal and postmenopausal. And even though we have most of the independent postmenopausal cases, we have still quite a lot of them in the premenopausal cases, something that was not expected at all. So again, our study is showing us something different that the literature says. And as a corollary of all of this, I think it's also clear that not because you have lesion necessarily implies that you will have ovarian cancer. So that's good news. But then why stop there? We have this information, this 3D morphology of each and single lesion in each sample. So what we decided to do is to take several measurements, 15 features to be exact, that I had to do with the geometry, the intensity of the Ki67 and p53 immunohistochemistry, and the cell count and density. And I want to be very clear again, this data has never seen before in 3D. So we were presented with an unique opportunity to apply clustering algorithms. So what we did was to, of course, anyone familiar with data science knows, standardization and PCA to get the most important information from these features. Then we applied clustering algorithms, and we got this result that it's in high dimensions, but we were able to visualize in 3D thanks to the UMAP algorithm. And as you can see here, these 10 groups represent 10 different phenotypes. That is way more than the original 3 that were believed. And I can show you 2 examples here. These 2 were classified as tick according to the literature classification, but I can assure you they are totally different, especially because of their geometry. That one is over 1 millimeter long, actually. It's the worst one that I already showed you before. The one on the right, it's just 200 micrometers long and with a way fewer cell count. So I hope this gives a clear impression. This is the Ki-67, so you will believe me that it was a stick. So they are quite different, and we have a lot of new information that will quite change the paradigm right now in the literature. So there are not 3 main phenotypes. And we can use this to conclude. So by developing the first 3D single-cell resolution map of human fallopian tubes, we're able to see that there's a massive incidence of lesions, that it must be rare they evolve to ovarian cancer. They can be found all over the fallopian tube. They are present at all ages. And I'm sorry about that, but there are 10 different phenotypes. So these discoveries could really change how ovarian cancer is treated in the clinic, because having lesions does not imply that you have ovarian cancer. So the real question is, which lesions evolved into ovarian cancer and under what circumstances? And that's the future work that we are planning to do. Spatial transcriptomics, proteomics, and metabolomics on these lesions will allow us to identify the pathways that the cells follow. So thanks to everyone involved in this project. And this was the presentation. Thank you.
Thank you, Alfredo, for the great and scary talk. Anyone has questions? Okay, I'm going to go there first.
Thank you, Alfredo. It's really impressive, your work. Congratulations.
Thank
first. You. I have 2 very short questions. One is, this is quite impressive, but it's sort of ex vivo, right? You have to extract the fallopian tubes.
Exactly.
Have you thought, or have you seen in the literature any work using nuclear techniques, nuclear in the sense of radioactive, like nuclear molecular imaging, that could be useful to identify these precancerous lesions?
I haven't seen anything in the literature like that, and I'd love that exists, because as you so sadly these samples were from deceased patients. Yeah. It's not, of course, it's not common to have the fallopian tubes extracted. Nowadays, it's something that we are seeing more in the clinic, because since now everyone, every doctor knows that if a patient, a woman, don't have the need, they don't want to have kids, for example, or they don't really need the fallopian tubes, they will advise to extract them if they undergo any other type of surgery in the abdominal area. So to answer the question, it's not common for someone to get a diagnosis of lesions. So yeah, no, not that I'm aware of. There's not a way of really seeing them without extracting them and do this type of techniques.
The advantage would be it's non-invasive, and it could be informative. And my second question, I think you answered in your last slide, is what do you think would be the steps to take this towards sort of a translational path?
Yeah, getting biomarkers for sure. Getting biomarkers, that's the goal now. We want to get information that we can measure with any kind, because biomarkers, it's a whole world, but if we can get any kind of molecular information from the cells, from the sticks, for example, then we can see if that could be detected somehow in the blood or in any case.
Maybe even by nuclear imaging, think of it.
Yeah, I have to delve into that actually, so thank you. Ines?
Any existing technique like PET scan, MRI, CT scan simply do not have the resolution to. These are all macroscopic. They come from 10 micron, 100 micron to millimeters. They simply would be undetectable. That's why the Pravda line about the occurrence is 0.01%. We discovering is 100%. And that's because not of lack of attention, not of lack of trying to detect those, they simply were invisible using classical ex vivo, or rather in vivo imaging techniques. So, this is game changing, just to be clear. This is, we're all walking around with mini tumors in all organs. I think that's just an example. We had observed, Ashley had discovered something similar for the pancreas. It is highly likely that every single organ have such mini tumors, which is sobering thought, but that means automatically, exactly as Alfredo explained very well, the probability of such a lesion to turn into a full-blown tumor has to be minuscule. We're flipping the paradigm. The paradigm, as soon as you have a lesion, you will have a tumor, you will have cancer, is simply completely wrong. It has to be wrong. Not all women are dying of ovarian cancer, so that's the simple math.
Thank you. Any other questions, anyone? Oh, sorry, Vasco.
Congratulations, Alfredo, for your thesis and for this great presentation. I guess my question is, you mentioned that all of those stacks that you generated for each potential lesion that you generated automatically had to be manually curated. Could you explain a little bit more as to why you had to do that and what goes into manually curating what looks to have been a lot of potential lesions? Thank you.
Yeah, that was crazy work, actually. We ended up finding around 100 lesions, and we manually checked around 1,200. That's because the algorithm is not perfect, of course, and that's not necessarily a bad thing. So first, the same thing that Ines said before, we are cutting every single slide from the fallopian tube, but we are not using every single slide. We are skipping one, because then those slides we are going to apply special transcriptomics, metabolomics, etc. So we're undersampling too, even though it's minuscule, it's still undersampling. Furthermore, IHC is actually not used every 2 slides, it's used every 8. So that gives a small error that for one side could be seen as something bad in the sense that we are not precisely identifying lesions. On the other side, as I showed you before, how can I, here. No, sorry, I think I don't have the PowerPoint, but what I wanted to say is that, yeah, I think this will work. We don't only have sticks. Sticks are this one that have positivity for the 3 things we're looking for, but we have stills and p53 signature. So if the program worked perfectly, we had these perfectly accurately measures of IHC, we would only identify sticks because the connected components, the combination of these 3 images, would only identify this. It will completely ignore these cases. So in a sense, we embrace this part of the algorithm to be sure that we're not missing lesions. So it was a lot of work, but it was completely worth it because that way we are completely sure we are not missing anything.
Okay, thank you very much.
Thank you.
Thank you. Okay, so we're running a little late, so we're gonna go now to our lunch break. If you have your lunch ticket, please find Margarida on the right side of this, sorry, your lunch bracelet, wristband. The lunch will be here on the right side. For those who did not sign up in time to get lunch, you can still see if there's anything left from people who didn't show up. Yep, I got the confirmation. We do have some lunch boxes available. So first come, first served. Go talk to Margarida in the back if you need a lunch box. Otherwise, feel free to walk to the right side. Have a nice lunch break. Remember to go visit the posters. We kindly ask all the poster presenters to stand by their posters. Our judges are gonna come by, okay?
Also, for those students interested in coming to Hopkins, please talk to Ines, Alfredo, the newest alums of the group, but of course Andre, Leonor, you can, you're part of the gang. Vasco, Ashley, myself, Ines, please use the fact we're all here today to maybe, learn a little bit more about the program. And you're going to give me the...
A little. Okay. Okay, we'll resume by 2 p.m.
Please come back.
Yeah, 14 hours, 2 p.m. more or less, okay? We're gonna resume our session. Olha, este microfone ia
Vai dar resultado, mau resultado?
Eu vou deixar ali em cima também, está bem?
Ok, obrigado.
Ok, a Leonor está aqui. Good afternoon, everyone. We're going to resume our activities. Please take a seat. Thank you, everyone. I'm going to call to the stage Vasco Queiroga. He is currently a PhD student at Johns Hopkins, and he is also a former HOPTEC student from 2 years ago. He did an amazing job and continues to do. So Vasco, please.
Hello. Hello, everyone. Thank you very much, Ines. And welcome, everyone, to this panel titled Engineering New Paths to Health Solutions. It will be my great pleasure to present both Professor Cláudio Lobato da Silva and Dr. Leonor Guedes da Silva. And first up is Professor Cláudio Lobato da Silva. Professor Cláudio Lobato da Silva received a diploma in chemical engineering from Instituto Superior Técnico in 2001 and got a PhD in bioengineering in 2006, also from Instituto Superior Técnico, in collaboration with the University of Nevada in Reno, USA. Presently, Professor Cláudio Lobato da Silva is an associate professor at the Department of Bioengineering here at Técnico, and her research interests include expansion of human stem cells, cellular therapies with and genetic engineering of human stem cells, and also bioreactors for stem cell culture. Please join me in welcoming Professor Cláudio Lobato da Silva.
Thank you so much, Vasco. Thank you. It's really a pleasure to be here in this first HOPTEC seminar. And it has been a pleasure also to participate as part of the scientific board of this initiative. Thank you especially to Ines and André, who are the original ambassadors. And then we have now lots of other students coming, but it's really a great pleasure for me to be here. So, my idea today is to share with you some of the research that we do at IST in this context of cell-based therapies, namely to address some unmet medical needs. And starting by what is an unmet medical need is hard to define. There is lots of literature about it and the different definitions. I would say that the more consensual definition ends up by taking into consideration the overlapping in and depending on the alternative treatments available, either the disease severity and also the characteristics of the patient population. In Europe specifically, there has been an increasing awareness to the need of establishing these new advanced therapies to meet these unmet medical needs. Why European Union should invest more, and the European citizens are really keen in we should invest our money in more treatments and better treatments for different conditions. And advanced therapies, as these advanced therapy medicinal products, are considered now potential game changers in modern medical care with a huge impact for patients and society. In one consortium, a recent consortium that basically involved a survey to a significant proportion of the European population, people identified as one of the most important societal topical the healthcare. And people are convinced that we should invest more in these advanced therapies. Among this category of special therapies, gene therapy, cell therapy, tissue engineering. So this has been the most commonly targeted therapeutic areas, namely cancer, rare disease, neurological, diseases related with hematology. But regardless of the new treatments that you might consider for these conditions, you will always be challenged by lots of problems in clinical translation. One of our favorite challenge in clinical translation is the scalability. So as an engineer, and my background is on chemical engineer, so the scalability, how to deal with the difficulty of having a reduced number of cells and in order to have clinical relevance. The materials that you use to cultivate the cells, which should be compliant with regulatory standards. Defining if the therapy that you will use cells from the patient, will use cells from a matched donor. Even the way that you will administer your cells into the patient, and at the end of the day, really critical, it's really hard to define what is the true mechanism of action of the cells that you are infusing into the patients. So at Técnico, part of Técnico, our research unit, the Institute for Bioengineering and Biosciences, and our lab at Tagus Park, the Stem Cell Engineering Research Group, we have been trying to identify specific microenvironments in which stem cells and primitive cells in general reside. And basically, we try to develop and establish new processes for the cultivation of those cells towards the development of those advanced therapies that I just mentioned. We have gathered significant expertise in different tissues, namely the umbilical cord, the bone marrow, more recently the bladder, also muscle tissues. Then we develop protocols to isolate these cells from different origins. Then we establish methodologies for the expansion, that is the multiplication of these cells in the lab under controlled conditions, hopefully using these technologies of bioreactors. And then in some cases, we can even consider the new paradigm of, rather than using cells, using agents that cells produce, namely exosomes or other cell-based materials in a cell-free therapy. For this short talk today, I decided to show you one of the flagship projects of Técnico related with a new program that we established based on muscle cell tissue engineering, okay? So we have been gathered significant expertise in the skeletal muscle manufacturing, but also smooth muscle cell manufacturing, based on our recent experience in two European projects. And I will share with you one of those European projects funded by Horizon 2020 is the AMELI project, which stands for Anchored Muscle Cells for Incontinence. It is a big consortium with more than 13 partners. It's coordinated by the University College London. And the motivation underlying the project is a condition that is not neurological, it's not cancer, it's a condition that is associated to a huge stigma that severely impacts the quality of life of patients, affecting almost 70 million adults in Europe. And by adults, we are not talking only on the elderly, okay? We are talking of young females that upon birth and vaginal delivery might end up with this condition, fecal incontinence. And the current management of these patients is clearly unsatisfactory and represents an unmet medical need. So we can have the diet changes, bowel training, also other treatments that do not solve the true problem of the lacking of the function of that muscle. So regenerative medicine's approaches are needed. In this case, we want to solve the problem associated to a sphincter that is composed of both skeletal muscle and also smooth muscle and also nerval cells. And basically, we have several clinical trials going on for urinary incontinence and also for fecal incontinence, but always relying on this ability to release cells alone, suspension cells, and basically this is not the natural way that the cells reside. So typically the muscle cells are cells that depend on being attached to a tissue, to some material. So by infusing these cells in a free mode, okay, the cells are associated with a huge reduction in their viability, compromising the viability of the treatment itself. So this European consortium targets the development of an innovative approach comprising skeletal muscle cells, okay, combined with a biomaterial, implantable microcarriers, implantable spheres that can enable the delivery of these skeletal muscle cells into the sphincter, into the damaged muscle of these patients. So this will be the first time that these implantable microcarriers will be combined with the cells for this clinical setting. It is an approach that uses the patient-owned cells, okay, it's an autologous trial. And basically the opportunity for IST here as an engineering team was to establish a bioprocessing strategy for the manufacture of that combination of having the cells plus the implantable microcarrier. Ultimately, and this is one of the important features of the whole consortium, is that at the end there will be a clinical trial, okay, showcasing the delivery of these skeletal muscle cells into this natural state of being delivered combined with these spherical particles. So the original strategy comes with the knowledge from University College London, in which implantable and biodegradable microcarriers made of a very popular material, PLGA, were developed. And in fact, this material was granted with a special regulatory authority authorization to be approved for human use. Then there was also within the consortium know-how about the management and the processing of these skeletal muscle-derived cells. And at Técnico, we had a huge expertise on using reagents, defined reagents for the cultivation of stem cells in general, and progenitor cells as well. So for us, it was quite logical to take advantage of some of the advances that we had at IST, but this time to cultivate these skeletal muscle cells. So for instance, one ingredient that we have been gathered significant expertise on is these platelet lysates. So some of the platelets that do not end up by being infused into the patient in a transfusion strategy as an off-the-shelf product. In fact, these off-dated platelets are sent to garbage. The thing is, these platelets can be used as a supplement for the cultivation of cells, with a good advantage over the fetal bovine serum, which is a common reagent that people use in clinical trials and in the cultivation of human cells in general. And this way you can avoid the problematic issues of an animal origin product, namely the safety, risk of contamination, and also animal welfare issues, okay? So we consider to use this supplement for the propagation and multiplication of those skeletal muscle cells. Then most of the approaches use a manual combination of putting the cells in contact with the microcarriers, the particles itself. So we developed a strategy in which those cells were combined with those biodegradable particles in a bioreactor. That is a more inventive device. Okay, in this case you can see how this works. So basically this is a tiny setup, okay, a tiny stirred vessel in which you can combine the particles with the cells, with the skeletal muscle cells, very effectively, okay, with all the mixing for homogeneous conditions in the system. So this is the schematic setup, okay, so you can start by expanding the cells until you reach clinically meaningful numbers for the transplantation that you are intending. Then you can combine in the bioreactor the implantable biodegradable microcarriers with the skeletal muscle cells. Here there was a huge effort in optimizing what would be the best conditions to maximize the levels of attachment of the cells to those microcarriers. And voila, at the end we have this combinatorial microcarrier cell-based product, okay? So we tested these for different donors, okay? This is really important in order to plan the clinical trial, although this would be targeting young females, but there will always be some variability from donor to donor. So we tested these for different donors, and we could see that an incubation period of 24 hours was the best one to promote attachment of the cells into the microcarriers, okay? And here you can see some of the controlling readouts that we use to make sure that the cells are attached on the microcarriers, also using DAPI staining, and also here identifying some focal adhesions, so the attachment of the cells to the matrix entrapped in those microcarriers. And at the end, we have to make sure, and this is really important to proceed to the clinical trial, we have to attest the cell identity, the identity of the product that you are developing in the lab. So one of the techniques that we use to demonstrate that our skeletal muscle cells at the end of this process are still the skeletal muscle cells is the flow cytometry, and one of the readouts that has been commonly used in clinical trials is the expression of the skeletal myoblast phenotype, which is CD56. And here you can see that we do not have, it is not affected the levels of the expression of this marker with the expansion and the incubation period inside the bioreactor. So this is a good thing. And then we can also try to, and we establish a readout in which we demonstrate the muscle differentiation potential of the cells attached on those microcarriers. So basically, at the end of the culture, we can harvest some of those particles with the microcarriers. We put those into a Petri dish, then we allow the cells to spread out of the microcarriers to populate the dish, and then by playing with some differentiation conditions over control conditions in the absence of differentiation stimuli, we can demonstrate the formation of multinucleated myofibers under proper conditions favoring differentiation. And basically this attests the identity of our product upon the manufacturing of that cell microcarrier combination. So the conclusions is that we were able to optimize culture conditions in the bioreactor setup to obtain a robust percentage of viable cells attached on top of those microcarriers. The adhesion process was completely devoid of animal-derived components, which is really important in order to assure GMP compliance, that is, compliance with the regulatory hurdles for clinical implementation. And also an important feature is the bioreactor. Basically, that setup that you saw is a single-use bioreactor, so each patient will have her own bioreactor, and the cells plus the microcarriers will be harvested and implanted into the site of the injury, okay? So the technology established by the IST team was recently transferred to a CMO, a contract manufacturing organization in UK, which is the National Health Service Blood and Transplant in UK. And basically, we are now starting the enrollment for the phase 1/2b clinical trial of autologous skeletal muscle cells combined with the microcarriers for the treatment of fecal incontinence in young women with a sphincter injury, okay? It will be a clinical trial with 30 patients. So I hope that I convince you, and this is one of the take-home messages, is that since the very first beginning in which you have a great or in a very promising cell population, a stem cell population or a progenitor population with a great therapeutic potential for clinical use. Until the generalized use of that therapy, it is a long path to go. Lots of challenges, more associated to the manufacturing, more clinical associated challenges, and that's why, and this dictates that we still have very few cell-based products available in the market, but hopefully with the completion of this clinical trial, we will have the chance of providing a new medical solution for patients that do have an unmet medical need, in this case related with this incontinence. Finally, let me acknowledge all the team that participated in this project, the Amelie project, okay, funded by the European Commission, all the team at IBB CERG group at Tagus Park, also Professor Joaquim Cabral here, who was the coordinator of the Amelie project here, the representative of IST, and also we have here one of the postdocs involved in the project, Teresa, that contributed a lot for the success of the project, and this is one of our recent photos of the team. We were missing a more recent photo, so basically we have it here, and thank you so much for your attention, and I'm happy to take any questions. In the day. Okay, good. Okay.
Hello again. Please join me in thanking Professor Claudia one more time for a great presentation. Thank you very much. So we'll now have one more talk, and then at the end there will be a time for questions and also a time for some discussion on this very relevant topic of how engineering can help forge new paths to health solution. And now please join me in welcoming Dr. Leonor Guedes da Silva. Dr. Leonor Guedes da Silva has obtained an integrated master's degree in biological engineering here at Técnico in 2014. In 2012, Leonor worked as a student researcher at TU Delft, and subsequently she served as a visiting student researcher at Johns Hopkins University to conduct her master's thesis dissertation in prostate cancer in the Wirtz lab. As you've heard before, Leonor was one of the first students, or the first student, to actually make this bridge between Técnico and Hopkins. And so that's when it happened. In 2019, Leonor got her PhD from Delft University of Technology, and after that, she joined DSM Firmenich as a data and modeling senior associate scientist. In 2022, Leonor transitioned to the role of R&D manager for lab data automation and analytics and early stage tech platform director. Currently, Leonor is a data and AI lead and digital product manager for science, innovation, and labs. And in her role, Leonor bridges technology, data, and user experience design to create scientific digital products and data strategies that align with both business priorities and embed data governance by design, and ultimately drive competitive differentiation through digital systems and AI. So please join me in welcoming Dr. Leonor Guedes da Silva.
Funciona? Okay. Bom, segunda vez que tenho a oportunidade de falar, estar aqui hoje. Eu queria agradecer imenso ao convite para estar aqui, pelo diploma, o certificado. Acho que vou emoldurar e pôr na minha parede, e talvez para me relembrar todos os dias que temos que sair da nossa zona de conforto e dar aquele passo no desconhecido. E realmente conseguir alcançar as nossas ambições. This was a little Portuguese note for the organizers. I really appreciate it. So I guess what I wanted to share here with you today is what I wished I had known before. Because, you know, great things you can see probably the good lessons through the LinkedIn profile or some other talks. But today I wanted to just share with you maybe the things that I wished I had known and done differently. And one of them is So in the Netherlands, we have this common thing during our PhD that we come up with propositions. So I came with a couple of propositions for you today, and you can oppose to those and challenge me on those. But let's see how it goes with the discussion. So typically in a career path, it is easier to connect the dots when looking backwards. And if you look at curriculums of everyone, it all makes a lot of sense. Wow, this person really knew exactly the path to go through. But actually moving forward is a lot more opportunistic than planned. I guess I didn't know that I was going to serendipitously bump into Dr. Wirtz here at Técnico, and that would unlock all sort of opportunities. So let me pinch. Yes, 10 years later, and here we are here with a HOPTEC program. I don't think both Dr. Wirtz and I ever thought that we would evolve into this, but definitely 10 years ago or even before, it already made a lot of sense that this bridge was there and was created. So, you know, I drew a little line through all of the things that I was doing until now in my engineer and scientific brief track. And, you know, at some point, some people thought, okay, you're jumping left and right into different type of bio topics. But what is it that is sort of the red line threading through all of this? I took some years to finally figure it out. But eventually I found out that every time that I was entering a lab, I was wanting to already combine the bio with the engineering, but I was also very much interested in combining the experimental side of things with the computational side of things. And when you try to do that, you understand that one of the things that is most important is that the data that you generate in the lab is of very good quality, because whatever you are going to do downstream for that with your models is going to define whether you're going to be successful on that or not. So I've done a bit of bioprocess lab experimentation, had a short stop over summer at INESC for microsystems research there, the PCR on the chip. Then ended up in Johns Hopkins for my thesis, and we did a lot of beautiful microscopy images, which I got reminded today how beautiful they are. But a lot of, I think what really stuck with me was this whole concept of high throughput cell phenotyping, because we can apply all the omics we want, we can sequence as much as we want, but in the end of the day we need to understand what the cells are actually doing. And I think phenotypes there played a very important role for me. I was not super comfortable with the way that we were handling cells in the lab, so I needed to do my systems biology study in a system that I felt was a bit closer to nature. So then that's what took me to look into systems microbiology, into microorganisms that naturally lived in suspension and could deal with a bioreactor in the lab, and just to be sure that whatever data I was generating was a bit more representative of their natural habitat, and really looking into how can we connect all this phenotypic data to the genotype or the transcriptome data. Then this is when I sort of got out of academia and joined the DSM. That's a company just across the town in Delft from the University of Delft. And there what I really wanted to, I left the lab because taking care of a reactor is like taking care of a baby. It requires a lot of attention. So I thought, okay, I just go behind the computer 100% and make sure that, I give the attention needed to all of these. And then basically my job there was to liaise with all the different biologists or engineers that were doing things in a rather traditional way and understand how they could do best use of the data they were generating and create novel approaches to the way we do science. So this was all good until 2022, and I'll get to the next bit in a while. But just to give you an impression of what is DSM or DSM Firmenich now, since we undergone a merger, we are talking about a company that is continuously striving for transforming the way that certain things are done. Typically, you don't know the company because it's business to business, so you see it behind the bigger brands. But for sure, if you buy any products on the supermarket, for example, from Unilever, you're probably consuming one of the molecules that our company produces. And there what we are looking for is every single time looking for molecules that can contribute to good health, but at the same time, can we not only contribute to nutrition, but can we also make it delicious at the same time? Looking into how can we support people improving their lives throughout their journey from early stage to healthy aging. And more recently also with the merger from Firmenich, we also got closer and closer to perfumery and beauty, which my first reaction was like, okay, now we sell perfume, so what is it that we are contributing to better health? Until I understood, for example, the connections with insect control. How can we use fragrance, for example, repelling also insects? For example, for stimulating well-being and contributing to a better mental health, how can we have better moments or be more focused or any other type of applications? So that was also very interesting insight for me personally. And I guess I already alluded a little bit to it, but what we are looking is really for the sweet spots in between three big pillars. One of them is all these essential molecules that we need and rely on every single day for surviving, let's say, that we individually need, but combining at the same time. I mean, probably no one really feels very motivated intrinsically to do the best for yourself, but hey, if the food that you love to eat, for example, or the products that you love to eat, already combine it with the things that you need, then you're combining the essential with the desirable. And of course, then there is also a big component to, can we manufacture all of these in a sustainable way that is not harming our planet? So every single time we are looking for alternative processes that are more friendly for the environment as well. So that sweet spot is where we aim to be the majority of the time with our product. And to back all this up, we have quite a big, and we are quite proud of it as well, quite a big science and research community with over 2,000 people across various different capabilities. So you can think of the more, let's say, mature technologies as chemical and processes sciences, analytical sciences, formulation sciences, nutritional sciences, but also the more emerging areas that are evolving, biotechnology being one of the examples that is very close to also what we do at Técnico, but other areas like microbiome and receptor biology and sensory sciences. And of course the data science and AI, and that's the part where I also I'm mainly active on, where we are really looking into how can we profoundly transform the way that our industry how our industry is operating today, and really reimagining our ways of doing science and research and development of these new products. Because in the end of the day, we want to be able to unlock some of the things, and I guess one of those that I wanted to highlight here, and I was thinking also of the work that Jude Philip was doing back in the days when I was also at Hopkins looking into aging. And hey, if we can not only tackle it in an active way, proactive way, how can we age well? And I guess Denis and Inez were also asking me, hey, you look the same, what is your secret? I don't know, at least sleeping well, I think it's a good one, but probably we can find us some options for this. So if I really now look back into what the company does and what was my trajectory, and I guess maybe in certain ways the little seed that Técnico planted in my head, that Denis planted in my head, was really to always look at how we are doing science and innovation and think of ways of transforming it and disrupting the status quo, and basically apply novel technologies, data, AI, to be able to improve the way of doing. And of course, I really wish and hope that we can collaborate more, not just coming together in certain events, but actually that technology enables a true collaboration across many different labs, institutions, improving the way we share knowledge, so that we can all, collective brain solve some of the big challenges that we face and society faces today. So now I took a little pivot or continuation or a refocus in 2022, and that's where I also went a bit from more my scientist role to the more management role, I guess. And I started looking into various different options. One of them that really also reminded me of my times at Hopkins was around lab data automation and analytics. So really being close to all the high throughput type of streams of data, and how can we automate analysis and kind of democratize it, because hey, we could have all a patient sitting next to us coding, right? But how cool would it be that we basically scale all the solutions that the programmers and the data scientists are creating for also all the rest of the scientists. And I was glad to see a couple of solutions also on the posters along those lines. So that's a lot of what my current role is really looking into how can we make this in a scalable way. Today I'm mainly looking internally in the company, but I think in the future I would love to really expand throughout the institutes and universities as well. So here's my second proposition. A good CV helps, but collaboration, networking, and references are way more powerful. And Denis already spoiled the story for me. I was going to tell the story of how you walked in, and no. But maybe I think it's a good reminder and just an invitation again for everyone that's here today to really just step out of your comfort zone and have a chat with various different people, because hey, you don't know if that's gonna get you at Hopkins next year, or maybe you can join the company I work for as well, or maybe some other institute, because our networks are much broader than just the institutions that we are here representing today. So really just get out of that comfort zone and try your luck. The no is guaranteed, so you can only improve from there. So hey. So what I find also important when you're in this type of connect, what type of investments you could do besides all the line items on a CV, is really working out on your personality, your human skills, your communication skills, and emotional intelligence, especially how you deal with situations of distress can be very useful for you as well. And these are the things that really matter in the interactions. No one is going to see those in a CV, so that's when you get out there, you really work on these skills and demonstrating them as much as you can. So my last proposition for today, knowing well your audience and your knowledge consumers gets you a long way with generating impact. And this is my invitation to you to also consider as much as possible to take the opportunity to do internships, to do exchanges, to do conferences, and simply reaching out. Not just for a chat, but really to be immersed in new environments, to be exposed to different realities, right? Sometimes at least I had that experience when I was a student here at Técnico. I was too much in sometimes my little bubble and thinking that this was the world, but the world is way bigger. And I think if you consider really getting out there, you tend to know much better what your audience is. So maybe it's your employers one day, maybe it's the person that's going to read your paper or that's going to listen to your talk in a conference. But really knowing them well, what are the challenges they're facing, what are the topics that are interesting for them, makes you much better informed on what are you going to do, what choices you're going to do, where you're going to focus, where you're going to put your energy on. And that way, hopefully, you also get more traction and generate more impact than if you were otherwise staying in your own bubble. So get out there. That's my final tip. And this is just a little summary. And again, thank you very much for the opportunity to present here today. But most important, I'm extremely happy that this program came to life. I think this is a very important bridge, and I can only hope that it keeps on growing and growing. Like Denise says, just a little factory, right? So hopefully it keeps growing. Yeah, thank you very much.
Please join me in thanking Dr. Leonor da Silva one more time. And now I would like to invite Professor Cláudio da Silva and Dr. Leonor da Silva to sit with me as we have a little bit more time for questions and also a bit of a discussion about the topics we just heard about. And so first, I would like to ask, does anyone have any questions to either of the speakers we have here today, either regarding their talks or about anything else? And if not, I have a couple of questions prepared myself, but please, Professor Wertz, let me just...
Two fantastic talks. Claudia, your talk was really inspiring, and you'll see immediately why when I give my little presentation on cell therapies. We need to talk. We don't know, we've interacted, and yet we don't know enough about each other, and I've discovered a lot more about what you're doing, and I'm sure it's a fraction of what you actually do. So nevertheless, I had a more technical question, and then for you, Leonor, I have a question about how you interact with other universities, but maybe let's start with you, Claudia. So I was trying to imagine the clinical scenario where you've now designed these bioreactors, and I think you alluded to it, right? You'd have basically for each patient an individual bioreactor. Can you elaborate on this, like paint a picture of how this can come about? Would you have in the basement of the hospital a bunch of bioreactors? That's what I'm trying to imagine.
Thank you. So the thing is, these bioreactors, the way that we have to select some bioreactors that would allow for single use, let's say, use it once in a GMP manufacturing scenarios.
Yes.
They are really appealing in a way that... Closer? It's okay. I can...
Yes, we can hear you.
Yeah. We do not have customized bioreactors for each patient. So they are equal. They are the smallest size available of that brand. Though they were originally developed by a company in US that developed an innovative way of mixing the cells in a, rather than a horizontal way to mix it in a vertical way, because they have been described that this induces less shear to the cells, okay? The good thing here is that being a disposable system is more amenable to GMP compliance for a clinical trial. And since our product is complex because comprises cells plus the particles, one of the features of the bioreactor is that they have a bottom port. So at the end of the culture run, you can open that bottom port and harvest the all contents of the culture device, and then to collect it in a syringe that then can be washed and administered locally with a special needle, okay, delivered at the site. But it's a small bioreactor, since this is an autologous trial. So each patient will receive roughly 100 million cells plus 500 milligrams of particles, okay? So a bioreactor like this that fits in a normal incubator, it's okay. And this will be done by that CMO. So we do have the CMO in place in Birmingham. So we consider that we will have a central manufacturing unit there, and then the cells plus the carriers will be delivered to the local hospitals for the infusion. Okay, so that will be the rationale underlying the clinical trial.
Wish you the very best luck for your success for this clinical trial. When you transferred the technology to UCL, had you filed a patent? You filed on process or whatever?
No, so it is. So we publish it.
Yes.
We publish rather than.
But before you published, did you file?
No, we did it. So it was we got a lot of input also from UCL. So we decided as an output for the project we we had the publication in place,
Yes.
the original publication. We did not patent because the bioreactor itself, it was from a commercial supplier.
Sure.
So we had that, and this was also a part of the success and the fact that it was quite straightforward to find out, because we were in a rush. Our deliverable in the clinical trial and so for a 5-year project, we had 9 months only for our work package. So we started and we already had that, so it was quite hard for us to put there. So it was an amazing team with a dedicated postdoc team. So it was the only way to do it, okay? And then now we are at the stage of discussing more the clinical part of the details for the trial. But probably next time, and this is a learning experience, so the patent could be more favorable in a sense. But this way, it was the best way that we had to proceed. Okay, it was the publication and the collaboration. 9 months, it was really hard for
pregnancy.
us. Yes.
And question for North. I don't want to monopolize the mic. I know, I realize, but I have to ask you a question about your, and I'm gonna make it brief. I saw in one of the words that I think you called yourself technical scouting, or I was wondering how you make yourself aware of the latest and most relevant technologies, including AI, in your firm. Do you interact with local universities, and how tight are the connections between your company and, say, Delft University and other European or even American universities?
Yeah. Well, at the moment, the biggest collaborations are rather local, right? So with Dutch universities, mainly TU Delft, we have 2 programs, one called AI for Bio and one called Genius. The last one is a consortium with more Dutch universities and really exploring what can we do with large language models, for example, for the different type of applications and scientific developments we have. Then we also have partnerships with EPFL, our, let's say, the company we merged with, Firmenich, is and these are the ones that I know by heart, but then depending on the topic, we have more specific collaborations as well.
Sorry, are there any other questions for either of our speakers? If not, I have a couple follow-ups, but please. All right, maybe my follow-ups will inspire some of you. So my follow-up is actually for Professor Claudia. I've seen those small bioreactors with the vertical agitation for reduced shear stress. I guess I've never really thought of it until more recently, but is there any way to monitor anything about the cultural, like, not even just pH levels and oxygen control, but also maybe some sort of monitoring of, for example, fluorescent signal? And I'll go into why I'm asking this briefly, but is there any way to monitor those cultures?
No, there is. The thing is, for those specific, as they come, they are really simple to operate. So you buy it and then you use it in the incubator. So basically you rely on sampling to do all the monitoring. But there are other type of bioreactor technology with fully controlled. So I never claim here that they would be fully controlled. The limitation here is that for that fully controlled bioreactors, you need other type of setup, housing in a manufacturing pipeline to do so. For this type of trials and manufacturing, the manufacturing pipeline would be heavier if you would use most complex setup of bioreactors. So in this case, the idea is to have very simplistic vessels that could do it in a disposable way, so you do not need to sterilize them in advance, so they come ready to use. You use to prepare the microcarrier and cell combination and then harvest. But the technology have evolved a lot from the chemical engineering and biochemical engineering sector, namely in the pharmaceutical companies. So we do have technology from Eppendorf, and we have it available in the lab, so it is much more amenable to optimization purposes that we are doing this today. The thing is, for the trial itself, it would be the best solution to be really easy to operate, okay, in a facility that they do not have any bioreactor experts, right? And with this single-use feature, which is quite great for GMP compliance. Okay. But for us engineers, it's quite a dummy system because it's like a black box, but you can have a fully control as soon as you have more sophisticated bioreactor setups.
Okay, thank you very much. So would you say that it's more of a, once you've optimized the system, you'd use that for someone who doesn't know how to optimize?
Yes, from then the idea, so you'd have all these, the innovation part and the processing development in our side. As soon as you transfer this to a CMO like we did, or any other CMO, it will be operated by technicians, not fully engineers, but you would have the fully optimized process in place, hopefully. But relying on different type of technology compared to this one. As it is, this is the simplest one available from that company, the smallest size, because otherwise, if it would be a bit costly, if you use a huge quantity of media, it would be even more costlier. So this would be the best match, the best compromise in order to turn this feasible and to assure any economical viability for the future, okay, outside the clinical trial.
Okay, thank you very much. Any questions from the audience? If no, I think we can maybe open a little bit more of a discussion into the key topic of this talk, which is the engineering new paths to health system. And so I have a question for each one of our speakers today. Let me just resort to my cheat sheet here. And they're more sort of a personal nature and also more related to engineering in of its own. And so I guess I'll start with the second speaker. So Dr. Leonor Guedes de Silva. And so we saw in your presentation that you've started out as a biological engineer and then you've moved through a series of other positions, some more related to one side of science, some more related to another side, and you've had success in a lot of different positions, including as a manager and more recently as a data and AI lead and digital project manager. So my question is, how would you say that your engineering background has allowed you to enjoy such a rich path in your career? And how would you say that that background and your path has allowed you to be a part of engineering new paths to health solutions, I guess?
Yeah. Well, I guess the engineer in me stays with me. It's always with me. It's just the job titles don't include it. But I think if I see it through, and now I don't know if it was a muscle that was created or can I attribute it exactly to my training, but just the incredible capability of absorbing any sort of new type of knowledge or approaches, right? So I'm not afraid to just have a conversation so outside of biology with someone that has a background on physicists or someone that has a computational background or someone that has now maybe a more management kind of background, right? And just understand all the different topics and have this constant understanding that these are all different parts of a bigger system and interact with each other. And you need to sort of, accept them and take them as a whole to be able to just progress, right? So the same way that, the topic of today is bridging between Técnico and Hopkins, and as we are having the different talks, we basically recognize things that could be interesting connections. I think that's where the sort of the engineering background plays a big role, right? It's not logical, it's not written next to each other, but your brain is just trained like that to make the connections. So I think that's, if any moment you feel like you know nothing, well, maybe you don't know a lot of a lot of things, but you have a good instinct, right? So just trust the gut then, I guess, and you will be able to, in no time, pick up new topics and make connections that others didn't see it before.
Okay, thank you very much. And I guess one final question to Professor Claudia, a bit in the same vein as my previous question, but how would you say that engineering, and in particular your background in engineering, has contributed to your role in the project that you were talking about, and also it seems that that's a very multidisciplinary team. How would you say that engineering played a role in the success, or will play a role in the success of that project and overall the outcome, which is a hopefully successful clinical trial?
Thank you, Vasco. So as an engineer, I think I'm moved by, I'm motivated by the challenging part of it. So we join a consortium with lots of clinicians. We identify, we were not aware of that medical problem at all. Every time that we think about incontinence, probably we are talking about the elderly, and then I realized, no, this is not only a problem of the elderly, and we do have even very young women with this problem just upon having a baby. So it's quite shocking that people do not have this as a solution. Then in a consortium of clinicians, some biologists, even patient association, being the engineer team there, it was really a pleasure, because basically we were the facilitators in terms of communication among even the clinicians and even the more the biology driven researchers. I think that we always have, and I was originally, I'm a chemical engineering by training. It was the course that then, the degree that gave rise to the biological engineering that presently exists at IST. But it was a training that provided us with a tool, set that basically gave us this opportunity of try to find solutions for problems. So you do have few cells. So what could be the strategy to surpass the challenge of the cell numbers? Then all the procedure, and they gave us a recipe. So with all the taking a close look, and in these the engineers take a close look and they map where the challenges are, and they propose solutions. And by my experience, I think that this is quite unique in engineers. Okay, I will not see our colleagues more from the biology side to having and ending up with these solutions arising. And the communication, we were also happy to be good communicators in a way of facilitating bridges at the end. I never wanted to be a clinician, but having a way of contributing to provide better solutions for the patients, so turns us very proud and very happy at the end of the day. Okay, so I think that this facilitator spirit, and also the troubleshooting, being driven by the challenges, I think this is really unique of the engineers.
Thank you very much. And please, once again, let's thank Professor Cláudio Abate da Silva and Dr. Leonor Guedes da Silva. I guess it does make sense that a bridge had to be formed between Hopkins and Técnico, two very good engineering schools, since, as we've seen, engineers are key to making or building bridges. And I'll now pass the word to my colleague, Andre.
Okay, so now I would like to welcome Professor Arlindo Oliveira. Professor Arlindo Oliveira obtained his bachelor's and master's degree in electrical engineering and computer science from the Instituto Superior Técnico, and his PhD from the University of California at Berkeley, where he was a Fulbright scholar. He was an invited professor at MIT and a researcher at INESC, CERN, the Electronics Research Laboratory in UC Berkeley, the Berkeley Cadence Laboratories, and the University of Tokyo. He's a distinguished professor at IST, president of INESC, distinguished visiting professor at Macau University of Science and Technology, member of the board of Caixa Geral de Depósitos, and a researcher at INESC ID. He authored 4 books translated into different languages and more than 200 articles in international conferences and journals in the areas of algorithms, artificial intelligence, machine learning, and bioinformatics and computer architecture. He received several prizes and distinctions, including the Technical University of Lisbon Santander Prize for Excellence in Research. Please welcome Professor Linde.
Thank you. Thank you. Good afternoon. It's a pleasure to be here. So I could give you an overview of the work that we have been developing in our group in the area of machine learning and deep learning, but I thought on focusing on a more specific topic, more closely related with probably the topics that you are interested in. So that's why I picked this, which is joint work with Tiago, Roxandre, and Lucas. The objective of the main objective of our group is to develop new deep learning architectures and try to address the limitations that existing systems have. Okay? And for that, in this particular line of research, we are looking for inspiration in the human brain, in the human cortex, and we are trying to use known features from the biological systems to improve the way, in this case, deep neural networks work. This is just a very small step towards getting systems that will one day, we hope, be able to have many of the properties of the human brain, of the human mind, but it's an interesting one, very focused on a particular thing. So we know that there are two main processing pathways for vision in the brain, the dorsal and the ventral pathway. The ventral pathway is mostly, this is all a bit messy, but is mostly related with object recognition. So the ventral pathway is the one that in the end enables us to recognize objects, while the dorsal pathway is more related with movement, position, situation, and so on. So this is rather well known. You can see there, I don't know if this is, you can see there on your right the dorsal pathway, and we are focusing on the ventral pathway. And what the idea for this research is to compare the way the ventral pathway in the human brain processes images, information, and the way deep neural networks, and in particular convolutional neural networks, but also transformer and transformer vision transformers, and compare the way information is processed in the biological pathway and in the synthetic digital pathway. Right? And the argument I'll show you evidence for that is that if you have if you process information in a way that is closer to the way the brain, the cortex processes information, then the tasks are, the performance is more robust. So you do a better job on most image processing tasks. So this is a cooperation with MIT. MIT set up this lab. And what they do is they do a number of recordings mostly from live monkeys. They also use humans, although there is not live recording. You just ask people to do tasks. You don't put electrodes on the brain of humans, only of monkeys. You record them in many conditions, in many tasks. Okay? Then you do the same thing with artificial neural networks. Okay? And you compare, by using the appropriate transformations, the sort of processing that takes place at each step in the transformation. Okay? And there is very strong evidence that as you have, so in the end you get from all these different tasks, I mean there are hundreds of tasks, from all these, you get something called the brain score. And the brain score is how close to the way a human brain processes information, or in this case primate brains, is your neural network processing information. Okay? So if you get a high brain score, then it means that the transformations that are being applied by layers of neural networks are closer in a way to the transformations that are being applied by the V1, V2, and so on in V1, V2, V4, IT in the cortex. And if you have a lower brain score, then it means that you are doing the things in a different way. Okay? And you can see there's significant evidence that as you get a better brain score, you also get a better performance in specific tasks. In this case, is the ImageNet performance, which is a classification task where you get basically to classify in 1 out of 20,000 classes a particular image. Okay? And you can see that the performance in the ImageNet has been growing steadily in the last 10 years. This is one of the pillars of the deep learning revolution, the ability to process images and so on. That was caused by the initial performance in ImageNet by AlexNet in 2013. But you can see, we don't have here time, but actually time is there somewhere because we have been improving these systems, improving in ImageNet performance, and also improving its brain score once you go back and try it. And so basically, this is the setup, right? So now there are, of course, many ways to try to do that, right? You can get inspired in different methods. You can use different layers. You can use this is an open system. Anyone can submit a new architecture to brain score and get your score and get yours in the ranking. Every 2 years, there's a conference to present these results and consign. So, but this particular work is a particular contribution. And so what happens is that current neural networks, they are not robust to a number of corruptions. So if you pick the original image and you corrupt it in a number of, by blur or by snow or release the console, there are many transformations. It turns out that neural networks get easily confounded. Even worse, they are very easy to fool by adversarial attacks. If you pick an image like this and you add this noise, okay, just this noise, it looks random, it's not random, it was noise that was picked up to fool this particular neural net, and this one is classified as an Egyptian cat, and this one, which to us looks like an Egyptian cat, is classified as a sleeping bag. Okay? Very sensitive to adversarial attacks, and we are not, basically. We and primates are not. I mean, you will not get fooled. To be fair, this is not a fair comparison because this particular noise was created to fool this particular neural network with a knowledge of the internals of the neural network. But still, we have reasons to believe we cannot do the same attack on the human cortex, on the human brain. But still, we have reasons to believe that the human vision system will not be so easily fooled. There are no adversarial attacks as simple as this that can fool the human visual system. Okay? And so those are the limitations of existing systems. And the research we are doing is basically trying to address these limitations by getting inspiration from the human cortex. This is the general setting, and I will now show you a couple of results. So the first was, I'll skip this. The first was, this is basically the same that I was saying, and the first was V1Net. V1Net was proposed in 2020, was a paper at NeoRIPS, and V1Net is basically a layer that is put before any standard CNN for vision, okay? And this layer uses a number of filters, basically Gabor filters, whose characteristics are obtained by inspiration from the first layers of the visual cortex. And you can actually put this V1 block before any CNN of any network of your preference. And the results, I will skip this detailed math. And the results, so it's filters like this, okay, that we impose. Okay? And then if you put this on before a network. For instance, on clean images, you have this is for instance ResNet 50. You don't need to use a ResNet 50. You get this performance. And on clean images, the V1Net plus ResNet 40 is slightly worse, right? You get from 74 to 72 or something. But then the performance on a number of noises, white box, corruption overall, you can see that when you put noise or adversarial attacks, actually the performance of the network with the V1Net before it is much better than ResNet, and is also in general much better than other approaches, than a ResNet trained against adversarial training, and then another architecture that was proposed. So the blue bar there, which is the V1Net before a CNN, even though it is slightly worse on clean images, it's much, much better on images corrupted or against adversarial attacks. So this was the first work done by Tiago, okay? They are better than all the state-of-the-arts, okay, this was in 2020. And what we have done more recently was to try to classify what sort of filters, what sort of these filters you should put there. And so what we did, this was the work done by Ruchandra. What she did was she carefully scanned the literature for the characteristics, the frequency characteristics of the filters that you have to put, okay? And then she created a layer, actually 4 families of layers. One that she called biological. So biological, the filters have the same characteristics. It says here that the Mac is going to sleep soon. I don't know if this is good. Let's hope not. So this one, the filters have the characteristics that are sampled from the biological networks. And then there is a number of simplifications where the filters are sampled from uniform distributions on the same range, where it preserves the spatial shape, and UNIF 3, where it preserves a number of correlations, in particular between the filter size and the spatial frequency. And the results are essentially that, so those are just examples of this. And the results are that on the clean image, as we know, there is a slight degradation from the simple thing to the V1 net. But then when you add noise or blur and so on, you can see that both the biological inspired network, which is the blue one, if you remove the exact distribution of the filters that you got from the biology, you get some degradation. But if you preserve, this is the UNIF 3, if you preserve just some characteristics, in particular the ratios of the filters and the relation between the frequency of the filter, you just preserve some characteristics that you obtain from the biological sampling, you pretty much keep up the same behavior. Okay? So the lesson is that it does improve the resistance against noise, different types of noise, if you use the exact distribution of biological systems, or at least as close as you can guess. But you don't need actually the exact distribution. You can do away with an approximate distribution that just preserves the ratios of the filters and the correlation between the ratios of the filters and the frequencies of the filters. Okay? So if you add this relationship between the size of the filter and the spatial frequency, recovers essentially the robustness that you obtained with if you use the exact biological distribution. Okay. The other interesting result is that if you look at those are in this space the spatial frequency of the filters and the sparseness and a number of characteristics, you can see that even though the distributions are different, but the results are actually very similar. So you don't actually need to have the biological distributions. So the second work we did on this, okay, what if we now add a retina block? That is a block that emulates the way the retina processes signals before sending them to the cortex. And that was the work of Lucas, okay? So what he did is he scanned the literature for the specific characteristics of the filters that are used by the retina before sending information to the LGN and then the visual cortex. And there is a number of details here. There are 2 separate channels for midget cells and for pyrosol cells. Those are just names that are given to these cells that have these center surround characteristics, okay? And then there are also 2 layers, a contrast normalization layer and a dog layer. There are some details here about what these layers do, right? So those are just the characteristics of the filtering. This was obtained from the literature, what we know about retina, and then he coded this as a retina block, and he put this, those are just the sources for the data that he obtained, right? For the midget cells, for the light adaptation layer. This is an attempt to illustrate the information that is done by the retina cells. Okay? Then the contrast normalization layer, another one of these data. Okay? And then it tried two things, right? So the V1 block was the one that we already seen. Okay, is inspired with the filters, the layer of filters non-trained. Then you try just the retina block with the same standard CNN. So this is the V1 block before the standard CNN layers. Then the retina block before the standard CNN layers. And then you combine the retina block with the V1 block. The retina, which emulates the processing done by the retina, and the V1 that emulates the processing done by the first layers of V1. Okay? And the results are interesting. You can see that on clean images, again, they are all similar, right? So this is the original CNN. This is V1, just the first layer of V1. This is RetinaNet, just the processing by the retina. And this is EVNet, which is the combination of V1Net and RetinaNet. And you can see that on clean images, they are pretty much, they do the same. But when you add different types of noise, both the V1Net and RetinaNet improve significantly on the bare network, but if you combine V1Net and RetinaNet, then you get overall much better results. So by combining the processing done by the retina and the processing done by the first layers of V1, approximating this as well as we can by looking at the literature, what sort of products, there are hundreds of papers written on this, you can get networks that are much more robust to noise and also to adversarial attacks, although I don't have those results yet. Okay? So all models increase robustness when compared to the base model, the gray one. There is a slight impact, negative impact on clean images, but then it's much more robust to noise, which is actually the characteristic that we are trying to look. We are trying to look at systems that are better in difficult conditions, which is where CNNs today work worst. We believe this has potential to have impact both on real-world images for applications like surveillance, or autonomous driving, and so on, but also on medical imaging. On medical imaging, that noise and removal of noise is important, so our work now is applying this to medical imaging. The interesting thing is that this actually can, there are a number of data sets that we can train, ImageNet-C, ImageNet-R, Tiny ImageNet. The backbone is not always the same. Here is ResNet 50, but here is VGG 16. And you can see that the overall improvements are reasonably consistent. The only situation where we did not see significant improvements was in stylized ImageNet. Stylized ImageNet is a very particular data set. It's not a realistic data set. It's a data set where images are replaced, for instance, by their contours, right? You take a cat, you just have the contour of the cat. You have a tree, just have the contour of the tree. So it's not a realistic setting for comparing against the human. We can still recognize a cat just by its contour, but it's very likely that this recognition of the image of a cat by just its contour is the result of higher level processing and not the lower level processing that takes place in retina and V1. Right? You need to know what the cat is to recognize a cat just from its outline. So it's not a processing that is done by the early layers of the cortex. And this is the only case where we did not see the stylized ImageNet, well, we did not see significant gains. So takeaway messages. Models that better approximate V1 are also more aligned with primate object recognition behavior. Adding a V1-like front end improves overall similarity both to the ventral stream processing but also robustness. It is not sufficient to approximate V1 with just general distributions of the filters. You have to have some approximation to the actual distribution of the filters that exist in V1. If you add the processing done by the retina with retina block, you get gains that apply on top of the gains that you obtain by using a V1-like architecture. And this is basically what I wanted to share with you. There are a number of papers on this. There is this NeurIPS 2020 paper that somehow started this. Tiago was at the time at MIT working with the group there. And then we have these two recent contributions by Rushandra and by Lucas on the contribution of V1 and of retina to improve CNNs. Thank you very much. sei se isto é capaz de não estar ligado.
So thank you so much for your amazing talk. I'm going to open the floor for questions. Does the audience have any questions?
Always inspiring, really amazing work. And I was curious if you, I don't know if it's called biomimetism, what you're trying to do eventually, right? Which is, but I was wondering if you could reverse the thinking. That is, any chance that you learn something about, for instance, vision or the brain and its architecture or its functional architecture from the neural net you're developing?
So actually the Brain's core project has these two ideas, right? I mean, I would say that the main idea is to improve artificial neural network architectures by getting inspiration from the human brain. But by mapping the activations of the neural networks on the human brain, you actually get a much better understanding on the way the human brain, the cortex, the visual cortex in this particular case, represents information as you go along. And this is probably not that very interesting in the first layers on V1 and V2, where we are talking about relatively low-level features. But I think it will be very interesting in V4, IT, and after that, where you want to understand how information is represented. And in fact, a number of my students they are working in particular with CMU on mapping. So when you use an artificial neural network, actually, especially transformers, the information gets mapped to an embedding space. And now that study is being done on how the embeddings of the artificial neural networks compare with the representations that you obtain by functional MRI on human brains. And the idea is to help us understand. And recent work on embedding interpretation, you can actually interpret what the neural network is thinking. I don't know if you have checked the very interesting work done on Claude by interpreting the internal representations of Claude, a very interesting paper by Anthropic that came out in May. If you have not ever put in Google Golden Gate Claude. So Golden Gate Claude is an LLM that was specifically designed to be always fanatic about the Golden Gate. So any question you ask it will put the Golden Gate on the picture. But that was just actually to show that you can not only understand what a deep neural network is thinking, but you can also manipulate its thinking. And so the idea is that we can now map internal representations, internal embeddings at different layers of the transformer network to the actual activity on the layers of the visual cortex, and possibly in higher layers of the cortex. And I think this is very interesting and very promising. I'll be delighted to give you a talk on this as soon as we have some more conclusive results, but so far it's looking very interesting. So we are looking at the way embeddings in transformer networks compare with the embeddings, with the activities on the brain. And so that will help you understand in the other direction, as you said.
Any other questions?
Thank you very much for the talk. It's from someone who has used some neural networks. It's very nice to see that it's nice to be exposed to the other side of things, which is not so much focused on the application, but more on the development. And with that in mind, I apologize if some of these questions are a bit more naive, but I guess my first one was, I found it very interesting that when you first showed the adversarial attacks, because that was something I'm not familiar with, and you said that there isn't anything equivalent in the brain that we know of, but I was immediately thinking of, for example, optical illusions and how it's basically a way of tricking the brain into seeing something that's not there or not seeing something that is there. And I was wondering if optical illusions would be the equivalent to adversarial attacks or something else.
I don't think it's exactly the same. Optical illusions, in most cases, it depends a bit. In most cases, it plays with higher levels of representation in the brain. For instance, the Necker cube is probably not V1 or V2 that is making the cube go back and forth. It's some higher level representation of a cube that goes back. That has to do with a very interesting topic that we're also working on, which is in the cortex, in the visual cortex, you have more connections going backward than forward. We don't know what they do. But all today's neural network architectures only have feed-forward connections. So there is an important role played by feedback connections, but we don't exactly know. We're also working on that, which is a really hard problem. But answering your question, I believe that most, probably not all, but most the sort of things you think, I think they are playing with higher level, and is the higher level representation that makes you, I don't know, the cube go around in one direction or the other, or the Necker cube. These adversarial attacks are very interesting because they are white box adversarial attacks. What does it mean? You have to know the network, you have to know the weights of the network, okay? And by doing that, you can mathematically figure what is the vector that you have, the vector is an image, right? The vector that you add to an image to make the classification go wrong. But you need to have the weights because you have to compute the gradient so that you know how to put this vector in the direction of the gradient, right? So let me explain this. This thing is saying it's a cat. You want it to say that it's a dog, right? So there is a vector that goes from cat to dog. Now you can see how much you have to change the input so that instead of getting a cat, you get a dog. So you need to, it's a white box attack because you have to know the internal parameters of the network. We cannot do that with the human brain because we don't know the parameters of whatever network. So we can try to do similar things, but it's like a blind search, it's a black box attack. So you can try adding noise and so on. But since you don't know where you are going, it's very, very difficult. The space is of very high dimensionality. So white box attacks against the human brain, the human cortex, as far as I know, are not successful. Now you can argue, yeah, but if you knew the parameters of the human brain, then you could have an adversarial attack, and just by adding a little bit of noise, you could get us confound the cat with a dog or the man with a woman. It's an interesting theory. Most people don't believe in it, so we believe that the system is intrinsically more robust and more robust to adversarial attacks. And part of the argument comes from evolution, right? If we had that, someone would have found that thing and found a way to fool the vision system, and the vision system has been around for a few 100 million years, so it's probably robust to that. So we believe that the primate and the vision system of animals in general is robust to this type of attacks. But it's not, it's not a clear-cut case. Maybe it is. Maybe if we knew the exact parameters of the visual system, then we could. But this work also shows it's not the case. If you mimic at least some parts of the processing that is done, part of it is low-pass filters and so on. If you mimic just some parts of the visual system, then you make it more robust also to adversarial attacks. So the assumption is that the human cortex, the visual cortex, and the human brain in general is robust to adversarial attacks, even probably white box attacks.
Okay, thank you very much.
I have also one question. Have you tried to apply these methods to semantic segmentation rather than just classification?
Yes, we do it too. We have been working on semantic segmentation.
And I was wondering, since you mentioned that these models are optimized to avoid noise in the images, you mentioned that you're applying it to biomedical.
So they are not optimized to avoid noise in the image. They are designed in such a way that they become more robust to noise in the image. We don't use the noisy image to train or anything. Actually, this system, the first layers are non-trainable. The first layers are not trainable, so those filters are fixed.
They're frozen?
They're frozen.
And how does it play with the gradient of the CNN? Because you made it
just goes through. The layers are frozen, but the gradient goes through, so you can still compute the gradients.
Okay, even with deeper CNNs?
Not a problem.
Thank you so much. Any other questions?
I was wondering if you could implement more layers similar to the ones that you implemented at the beginning, but in the middle of the network.
Presumably, each layer is more work, and the first layers are easier. So every layer that you go deeper is harder. What is happening as you go deeper is actually you are trying to use this. Map the internal representations. So let me explain this. So using fMRI, you can get actually the levels of activity in the voxel. It's a bit noisy, but you can get that, right? So then you can get that, you can process that, and you can embed that into a space of, let's say, 512 dimensions. Then you pick the 512 dimensions embedding of a visual transformer, and then you try to map the two spaces via linear transformation. If they map well, then there is a good mapping between the two things. If they don't map, then there's a bad mapping. But by doing this, you also understand, because what you cannot do on the human brain, you can do on the artificial neural network. If there is a good mapping, then you can imagine, okay, I can deduce that a dog is represented by this. And then you can show a dog and see whether the dog is represented. So this is very interesting work. So we are not doing it at the same level by reproducing the physiological components, but we are doing by the representation at the representation level.
Thank you. Thank you so much. Let's give another round of applause. So now we're going to welcome the second speaker of today, Professor Danny Wirtz. Professor Danny Wirtz is the Vice Provost for Research at Johns Hopkins University. He directs the Johns Hopkins Cancer Nanotechnology Training Center, and is the Theophilus Haley Smoot Professor of Chemical and Biomolecular Engineering in the Whiting School of Engineering. He's also an Associate Director of the Johns Hopkins Institute of Nanobiotechnology, Director of the NCI-funded postdoctoral and predoctoral training programs in nanotechnology for cancer medicine, and a member of the Johns Hopkins Kimmel Cancer Center. Dr. Wirtz earned his engineering physics degree at the University of Brussels in Belgium, and his master's in PhD and PhD in chemical engineering at Stanford University. Dr. Wirtz is a fellow of the APS and the AMB. He was elected as a fellow of the American Association of Advancement of Science for his contributions to cell micromechanics and cell adhesion. He was also distinguished for his development and application for particle tracking methods to probe micromechanical properties of living cells in normal conditions and disease state. Please welcome Professor Dr. Wirtz.
I'm freezing. I don't know if you're freezing. I'm very cold. Okay, you're cold? So hopefully we're going to warm up this room with some exciting results. But before we go there, I felt compelled to show you a little bit more how the campus looks like. And starting with on the left, the Peabody Conservatory. Men in the 19th century competing with one another by collecting old books. And Peabody had this vision not only to collect the old books, but to make these collections available to Baltimoreans, not Baltimoreans, right? Baltimoreans. And top right is the Evergreen House, one of those people competing with each other. We, by pure serendipity, collected and received as a gift to the university this house. It looks like a Roman villa. It has Modigliani's, Raoul Dufy's as part of the collection. In there you'll find original editions of, for instance, Vesalius atomical books, the Audubon elephant collections, these beautiful hand-painted books. This is medium right is just near our laboratory, and then bottom right is the hospital. So you saw the drone movie, but this is a still of it, and you can see where we are. And to ensure we not just have a nice, beautiful Georgian architectural buildings, this is the inside of the labs, right? We actually have laboratories in there, and we do some science when we can. This is Asini Jalatilaka, who helped develop bispecific antibodies, specifically targeting the onset of metastasis technology. We are now gearing up to test in clinical trials. But today I'm going to talk about CAR-T technology and all versions of it. So everything I know about CAR-T is what I actually do. Everything I know in immunology is what I do. Don't ask me questions on immunology that goes outside of what I'm going to present to you. So that's my way to say, hey, calm down, ask only easy questions. But conflict of interest, it's a good moment when you can actually talk about conflict of interest. That is, you actually a little bit entrepreneurial. You think about translating discoveries in your lab. I'm co-founder and investor of AbMeta. Ab, that's for antibody, meta for metastasis. We were not very clever, but that's the technology that was based on what Asini had developed a few years back. So today I'm going to talk about CAR-T technology. So the idea, and in a way, Claudia had a wonderful introduction to this. Cell therapies is the idea that is you'd harvest, in this case, a patient's T cells, that's one subtype of immune cells, and then transduce a CAR construct so that these cells can start expressing a CAR-T construct. This CAR is designed to recognize cancer cells once these cells are reintroduced in the patients. And they've been showing huge success in what's called hematological malignancies, a fancy way to say liquid tumors. Okay, that is leukemia, lymphoma. Upon reinjection of those engineered T cells, they have been incredibly effective at recognizing maybe cancer cells circulating in blood vessels, and our contention is that that was the easy part of the equation. That is, there's no physical obstacles that would preclude direct collisions between those reinjected CAR T cells and the target cancer cells. Okay? And indeed, now there's patients who've seen complete remissions over more than 10 years. The problem has been in solid tumors. That is, think of breast cancer, prostate cancer, pancreatic cancer, brain tumors, where this time those same CAR T cells you've just reinjected in blood vessels have to undergo literally a steeplechase. That is, they have to now extravasate out of the blood vessels, cross the base membrane lining this endothelium, go through a collagen-rich stromal matrix, cross yet another base membrane, and finally, if they make it so far, kill finally those cancer cells in 3. That is too much to ask, I would say, for those CAR T cells that were never designed to really, on top of being able to kill cancer cells once in physical contact with them, to before all that, do all those steps. And indeed, essentially all clinical trials of CAR Ts that were repurposed, being successful in hematological malignancies, are failing in solid tumors. Right? It's a big fat disaster, and before we throw the baby with the bathwater, we said, let's revisit and maybe add a little engineering flair to the question. So that is, can we find a way to make those cells go through these different compartments to then or use the ability of these CAR T cells to kill the target cancer cells. Before this, we needed to be very lucky. Okay? And you'll see lucky again and again and again. Maybe that's what it took to hopefully cure cancer. That's the observation that if you take primary human T cells, right, not sorted, you impregnate a collagen matrix, something you can do in the lab today. The purification of T cells is a fast process. Well, I might sit in my office and my students come on Friday. I have to presume this is easy. Of course, they do the hard work 24/7, right, Vashko? But if you look at those cells under a microscope at low density, that is far away from each other, they move very slowly. At high density, that is when the distance between them is now shortened, they move like crazy. Okay? Think of a phase transition in reverse. Right? So if you have gas molecule, they move a lot. They undergo a phase transition, they turn into a liquid, they move less, and into a solid, even less. Right? So kind of same cells, same collagen, just more of them, they'll start moving very fast. And indeed, if you take the supernatant of the matrix that has many cells and put them on the matrix that has few cells, off they go and start moving very, very fast. So we figured clearly these cells are secreting de novo new molecules at high density. And we had to identify those molecules. Before that, again, that's the data. These are staggering increase. I had to put this on a log scale because we see from 5 to 20-fold increase in motility. Right? If you had to come up with an ingenious way to make cells go faster, good luck. It's You think of making them more contractile, expressing actin. Well, that would give you 10 or 15% increase. We're talking about multifold increase in motility. So now we could have maybe the beginning of an idea of how to, in a way, capitalize on this discovery to move those CAR TV cells that I was talking about earlier. But before that, so again, we had to be lucky again. So we had a limited panel provided by my good colleague Rong Fan to identify what could be those molecules overexpressed at high density. Okay? It turned out to be IL-5, IL-8, TNF-alpha, interferon gamma. This was 40 molecule panel. These cells most likely express hundreds, if not thousands of molecules. Again, we had to be a bit lucky there. The idea is that, so we're observing that if you increase cell density, cells at low density don't move that much, and then at high density start moving a lot, okay? I'm just plotting that graph, trying to understand why these de novo expression of cytokines could trigger this high speed. So we also know that if you increase density, if you presume those cells just express at a constant rate these cytokines, you have a direct linear relationship between cell density and production of those cytokines. Of course, if you collect those two graphs together, here's your explanation. As you increase cytokine, which comes itself from increase in cell density, you're going to have the sigmoidal relationship between cytokine production and cell speed, okay? Which is exactly what we observed. Okay, so let's recapitulate this from scratch. Let's take cells at low density. They move little. Okay, that's the orange column on the left here. And we're going to add purified IL-5 or purified IL-8 or purified TNF-alpha or interferon gamma. And we can recapitulate, recover this high motility phenotype. Okay? Now, what's interesting is that if you look a little bit closer at your data, you recognize it's not that all cells start moving faster. It's you shifting the distribution from a low motility to a high motility state, i.e., even at low density, some of those cells move fast, but the majority of them move slowly. We're just shifting that majority of cells moving from at low speed to high speed. Okay? We can block and do all kinds of controls, including blocking interaction between those cytokines and the receptors. We can go downstream from this, block what's called JAK2 STAT3, which is downstream from those interactions, and basically convince ourselves that these cells at high density go faster by starting to express those cytokines. And indeed, not shown here, downstream from these cytokine receptors, JAK2 STAT3, you're going to have actin filament assembly, contractility that overexpress. I won't go into this. But now we know that these four molecules are necessary and sufficient to trigger this high motility phenotype. Okay? So now, that would have been a beautiful, finding, something you could package into a paper and be happy with yourself. But credit to my student, Adrian Johnston, to think beyond this. He said, can we capitalize again on this discovery to make not just T cells, but the CAR T cells go faster? And then we went crazy. Okay, he went crazy. That is, we have those four cytokines to which correspond four types of receptors. Each of these receptors will have a binding domain, an hinge domain, transmembrane domain, and a signaling domain. And we could maybe generate chimeras or chameleons, or whatever you want to call them, or synthetic velocity receptors. That is, where you can mix and match these different domains, and you discover, if you do the math, that you'd come up with about 31,000 possible velocity receptors. Okay? That is, instead of expressing these full-length receptors to take the advantage of the little they produce to hopefully trigger this high motility, we could express instead one of those 30,000 potential combinations. Now, velocity receptor sounds awfully familiar. It sounds like velociraptors. There's a reason. Remember that famous scene that scared the bejesus of anyone who saw this when they were 5? They're fast and they're lethal, right? We're going to turn these CAR T cells in serial killers that's going to go fast at it. They're going to kill everybody in sight, and that's mostly cancer cells. So we completely opportunistically decided to develop 5 possible velocity receptors. Opportunistically, why? Because that's what cloned well. That's what expressed well in the lab, not it was a strategic decision among the 30,000 possible combinations, okay? So here's the control. We're going to use state-of-the-art mesothelin targeting CAR T cells. That's Carl June's, pen down the road technology. Worked in lymphoma, lurked in leukemia, and failing abjectly in solid tumors. We're going to co-express one of those 30,000, or one of those, in this case, 5 velocity receptors. Okay? First control is to show that even at low density, when we now express this velocity receptor, you boost the motility. Now those cells are in a permanent high motility state. Remember, the control cells, or the CAR T cells, at low density, they still move slowly. We add this velocity receptor, and now they're always very, very motile. It turns out, remember I told you I was lucky, if you start digging deeper of why those cells move so fast, is that on the left, we made microchannels, is these control CAR Ts get stuck in these narrow channels, mimicking this collagen matrix. If we now add this velocity receptor, they go through, like it's butter. What we've discovered is that by expressing this velocity receptor, not only are we upregulating contractility and acting the filament assembly, we're allowing for those T cells to squeeze themselves through narrow channels that mimic this base membrane and collagen matrix. All right, let's move in vivo. It's time to test these velocity receptors. On the top is Carl June's control CAR Ts. In brown are a marker for leukocytes called CD45. And you see, if you squint a little bit of enrichment at the periphery of this tumor. These CAR Ts are stuck. They can't go in. They could smell the tumor, they were injected in the tail vein of these animals. They could go where the tumor was, but then got stuck. All velocity receptors, we co-transducing again CAR, but now we're adding this velocity receptor. That's one of them in pancreatic tumors, and it's massive invasion. Right? So does it work functionally? On top, on the right, no effect on tumor growth if you inject state-of-the-art CAR Ts. Same CAR Ts, but we add this velocity receptor, complete abrogation of tumor growth. Right? This particular mouse model of pancreatic cancer is very hard to achieve such a success, okay? Remember I had 5 constructs. They worked with different level of efficacy. But by and large, at least we had, for each of the indications, each of the type of tumor I'm going to be looking through, at least 2 constructs that work very well. But let's dig deeper. Let's look at this tumor more carefully. And what I'm going to show you is, again, is a controlled pancreatic tumor in these animals. In yellow are the cancer cells. Right? You see a little bit of red there. That's the few immune cells, the few CAR T cells that got close enough but never really got inside the tumor. And look what we obtain when we now add this velocity receptor. Okay? We went from hundreds of thousands of cancer cells present and unaffected by the treatment to complete eradication of the cancer cells. So this was bizarre, right? We could not understand why these tumors, which are not tumors anymore since there's no cancer cell left, still were voluminous, why they had not shrunk altogether. It's basically a complete replacement of the cancer cells by the immune cells. If you count, there's 13 cancer cells left. That's just after 2 weeks of treatment, which is nothing. Okay, you wait a little bit longer, and it'd be truly Hiroshima. They're all gone. Okay, and the reason, by the way, why there's so many immune cells, it's autocatalytic. The more you have them, the more they recruit more of them. So yeah, no chance left to those cancer cells. Does it work in other indications? This is lung cancer. Same massive invasion. The winning velocity receptor this time was different. Turns out. So we're going to have different optimal velocity receptor for different type of solid tumors, it turns out. This is good news in terms of business, I can tell you that. On the left was the state-of-the-art UCSF technology, where they try to engineer local proliferation of immune cells. Same pancreatic tumor, same animal, same everything, same duration of treatment, and on the right is all pancreatic tumor, complete, massive increase in infiltration. Because again, on the left, they never try to engineer truly invasion. Okay, does it help in the survival of those animals? Yes, 100% survival. And if you take those, no, I'll stop here, yeah, this is just a third demonstration in ovarian cancer. Any hint of toxicity, this is something you always have to worry about with immunotherapies. We looked at what you could look at. That is there off-target infiltration of the colon, the brain, the kidney, of those CAR T cells. And you can see, believe me, these graphs are complicated, that when you use CAR Ts, right, they get stuck, and then they do stupid shit. They start going off target because they're proliferating, and you have remember in COVID, you had cytokine storms? That's what happens. When you proliferate, they start activating each other, they start expressing cytokines, and then you have a high fever. That's what's been causing the failure of these clinical trials, is that these standard CAR Ts are not penetrating the target tumors. On the contrario, when you look at those CAR TV cells, we call them also CAR TV cells, massive infiltration and as I said, cell killing. So I'm going to stop here and acknowledge the people who did the work. Gretchen did the in vivo work, Adrian Johnson done the in vitro work, Vashko, who's taking the mantles already, massively improved the pipeline to produce different type of CAR TVs and different types of CAR construct, instead of taking us months, taking us days. I'd like to recognize also Vicky. We are going after every disease where a target has to be wiped out. Think of autoimmune diseases, for instance, lupus, rheumatoid arthritis. This time the target cells are not cancer cells, they are what's called autoreactive B cells. In rheumatoid arthritis, what these little bastards do is that to hide themselves behind the joints, right? You are treated with antibody, you wipe out the B cells of the patients. Over time, the good news, mostly the autoreactive B cells, the diseased B cells, are eliminated. The bad news is that the few that hide themselves behind this wall are unaffected by this antibody treatment. Well, we've just designed velocity receptors whose job it is to go through collagen-rich walls, and we want to wipe out those last remaining B cells. That's for autoimmune diseases. We can now look at cardiac disease, where this time the target cells is not B cells, is not cancer cells, it's cardiac fibroblast. After your first heart attack, you're activating these cardiac fibroblasts, they start spewing collagen, they rigidify the walls of your heart. What you want to do is to get rid of those. It's exactly what we have in mind here. We can use our velocity receptors. Of course, the core is not going to be mesothelin, it's going to be, in the case of autoimmune disease, CD19, in the case of cardiac disease, another CAR. But it's the same principle where we can use the chemotactic ability of this CAR T cell to sniff and find out where these cardiac fibroblasts are housed, and then just go through this protecting wall to now get rid of them. So I'm going to stop here. If you have any questions, of course, you can ask them here. If you're interested in HOPTEC, interested in this research, if a question to Vashko, please contact me, wirt@ghu.edu. We'd love to hear your thoughts about any of this. I'm going to stop here.
Thank you so much for the amazing talk. Let's open the floor for questions. Does anyone have questions?
Yes, please.
Thank you so much. Well, amazing talk. It's a very quick question. Are you following up with clinical trials on this?
So I'm looking at Claudia here. Yes, the beauty at Hopkins, I can line up a dream team. of amazing pathologists, amazing oncologists and clinical trialists. We will focus first with pancreatic cancer. That's actually where we saw the most efficacy of this velocity receptor construct. And I need to start a company that needs to then raise funds from a VC firm, so that's going to take a little while. Carl June is interested in joining forces, even though, when I talked to him, my first slide was to show how his velocity, his CAR TVs were not working, but was very happy to rediscover. He had developed a bazooka, he just forgot to bring the bazooka into the front. Okay, we have now an ability to put this bazooka on a truck that can bring it to those, to the front. So it's a beautiful partnership. Armed with this, we should be able to raise the funds to start a clinical trial at scale. But our first indication is this terrible disease, pancreatic cancer, life expectancy 9 months. You have maybe 8-9% survival in the US at least. So the standard of care is not changing in 20 years at pancreatic cancer. That's what we're going to start with. Yeah. But we have issues of cell manufacturing, it turns out, that I'd like to talk to Claudia about.
I also have a question. You showed that with these CAR Ts, you completely replace the tumor and you almost kill all the cells. I was wondering if you could expand a bit on what does this affect in terms of the patient care, replacing completely the tumors with just immune cells?
So it is now common practice to add in the construct, right? You have your CAR construct, we would add our velocity receptor to the third construct called a suicide gene. That is, you want to stop and kill those T cells once they're done doing their job. And so you can add this suicide gene. The good news, right, patients who 10 years after treatment with this CAR technology, leukemia and lymphoma patients, you still have some remaining CAR Ts in circulation. They provide in a way for vaccine. So any recurrence of the tumor is immediately addressed by these CAR T cells. So you don't want to wipe out entirely your CAR Ts, but you want to leave them a little bit. When those T cells in general are not stimulated to grow, they shrink back, but there's a memory left in a way in your system, and that's those remaining CAR T cells we want to use. So in our survival mice, what we need to do is to take them and re-challenge them with a tumor. Sounds nasty, but you go back with your cancer cells and now see if the few remaining CAR Ts can recognize this new tumor to preclude its growth. So that's another classical experiment to do, which we have yet to do.
Any other questions?
We just cured cancer. You should take a seat belt, enjoy the moment. These results are truly staggering. I'm boasting here, but it's just the way it is. It's truly special. I can say this, it's not my work, it's my students' work, but what you saw is actually not your typical scientific talk. It's truly special. It's a game-changing technology. I really believe this. Sorry, I shouldn't say this, but it is the way it is.
We're all good?
Yes.
Okay, let's clap for Professor Wirtz. Thank you both for those two excellent talks. So we actually have the coffee break planned right away, but due to some delays in our schedule, we apologize and we're going to move forward with the session just so our speakers' schedules can be maintained. And then we're going to do a coffee break, and then we are going to come back here for the poster and grand competition awards, okay? So let's keep this, sorry. And now I'm going to invite a few people to the stage. Professor Wirtz, you were just here, so please come again. Thank you. No introductions necessary since he was just introduced. We also have with us Professor Zita Martins. Thank you so much for being here. Professor Martins is an astrobiologist, associate professor and vice president for international affairs at the Instituto Superior Técnico, and a consultant for higher education, science, innovation, and digital transition at the Civil House of His Excellency, the President of the Republic. She graduated in chemistry at Técnico and obtained her PhD in astrobiology at Leiden University in the Netherlands in 2007. She was an invited scientist at NASA Goddard in 2005 and 2006, and an invited professor at the University of Nice, Sofia, Antipolis, France in 2012. In 2009, she was awarded a university research fellowship worth £1 million by the Royal Society, having remained at Imperial College in London from 2007 to 2017. From 2009 to 2023, she was co-director of the MIT program Portugal. Professor Martins has been at Técnico for a few years now, working both as a professor and a vice president, and she also maintains several space missions with the European Spatial Agency. Thanks for being here. I will now also invite, sorry, this is too many. Thanks so much. Professor Michael Boom is a non-profit management executive with decades of international teaching, research, and administrative experience between Europe and the US, actively engaged in building and strengthening institutional partnerships between Portugal and the US, particularly in higher education, and between the academy and civil society. Executive board member for the Luso-American Developmental Foundation, FLAD, and also an invited full professor and director of the Global Education Office for the Faculty of Human Sciences at Catholic University of Portugal. Thanks so much for being here. Let's clap, actually, for these two great participants. So sadly, Professor Rogério Colasso could not be here with us today, but we have Professor Zita, which is a great participation. I would also like to invite, in a very spontaneous approach, Professor Claudia Lobato. You're already here, no introductions needed, because she's been playing a very important role in selecting our students, and also Professor Ashley Keeman from Johns Hopkins. You can come, Professor Claudia. I'm now going to introduce Professor Ashley. She's been doing an amazing work with supporting our students while they're at Hopkins, and she was actually the argument for both theses of Inês and Alfredo. And so Professor Keeman received her bachelor's degree in 2016 from the University of Michigan Ann Arbor, majoring in chemical engineering. She then received her master's degree in 2017 from the London School of Economics and Political Science, majoring in philosophy. And she received her doctoral degree in 2021 from the Johns Hopkins University under the mentorship of Professors Danny Wirtz and Pei-Shun Wu in the Department of Chemical and Biomolecular Engineering. Since 2022, she has worked as an assistant professor of pathology, oncology, and functional anatomy at the Johns Hopkins University School of Medicine, and her research focuses on use of image processing and deep learning algorithms for methods development in 3D imaging and for the study of pancreatic cancer. Thanks for being here with us, all of you. Claps again. Okay, also invite Andrea to join, thank you. And so this is really a discussion moment. We welcome you all in the audience to participate. Vasco is going to be around with a microphone, so just wave at him. And Andrea is going to help me from over there with some of the questions, but please feel free to, jump in and give us your thoughts as well. Okay. Andrea, you want to start? First question?
Yes. So this question is for Professor Ashley, Dennis, and Professor Zita. As leaders in your institution, how can exchange programs like this one and official partnerships like HOPTEC contribute to advancing academic innovations? And can you share some examples of successful models or initiatives? I don't know if one says.
Maybe as the, is this on?
I think so.
I think I'm the least qualified, but I think I'll open. So I opened my lab at Johns Hopkins in 2022. And even in this small amount of time, I've had some studies that we had to go outside of Johns Hopkins to get things done. The specific example being we wanted to study some specific human tissue samples that have a mutation in them that causes these individuals to develop a disease at a high incidence. And these samples exist in a Dutch town called Leiden. And we spent months and months and months seeing if we could get all the legal documents done to get these samples to Hopkins so that we could analyze them. Because we have the technology and they have the patient availability. And it just was not happening. So finally I said, you know what, let me send my student to you, which, oh no, she had to go to Leiden. And I found that the best way to get it done was actually to establish a connection with this institution, that they had these unique access to these biological samples, they had all this knowledge. So instead of some legal documents and send us the samples in the mail, actually establishing this connection has, I think, helped the study in multiple ways.
Yeah, maybe Professor Words.
Yeah, that's a great, very pragmatic example and a demonstration that even with a huge university like Hopkins, you never have all the expertise, you never have all the reagents, support, and modern bioengineering and modern medicine require this multidisciplinary approach, and it's distributed excellence, and I see a lot of it here. So opportunistically, I hope our two institutions can come together even more so. I think HOPTEC is the perfect medium to make it happen. What I see a lot of excellence here is in both kind of indeed the chemical energy approaches to bioengineering and AI. And with those two tools, you can change the world. We hope that we can upgrade in a way and expand this program going beyond students, going from Technico to Hopkins. We were talking about this earlier, of now Hopkins students coming here, exactly what happened in Leiden with a student of Ashley, and build it from there. I think building it from the ground up matters. There's so much top-down programming you can do. If the faculty don't talk to one another and the students don't talk to one another, it's all going to be very theoretical. There has to be, therefore, trust building up, and trust can happen when you interact with one another. Trust that, that the Hopkins students will do their bit when a project needs to move forward, and know they're sitting on something, that they get it done. It's a priority for that lab, a priority for that student, and vice versa. So can we expand this program for research collaboration is really what I'm seeking to me as the definite mark of success of this idea that's now still bubbling up.
I agree.
Yeah.
So in my opinion, networks, international networks and innovation, they go hand in hand. I would like to give you an example. So we're part of this project called Widening. We were awarded 5 million euros. It's an Horizon Europe initiative. University of Lisbon / Instituto Superior Técnico is leading, is coordinating. So just for us, we received 1.7 million. And a large part of that money goes to 14 PhD scholarships. And so the students are going to be traveling between Técnico, our partners, which include some of the best universities in Europe, so KTH, UPC, Aalto, and they're also going to industry. So they're going to have the experience of being and doing research in academia, but also in industry. And so all this together, going hand to hand, you learn a lot about scientific excellence, about technology transfer, and innovation, which is basically your question. So for me, international networks, collaboration, everything is extremely important if we are to achieve our goals.
The easy stuff has been done. Now it takes teams to actually move the needle. Eventually for patients, right? And that takes. It's on bioengineering, not astrophysics. We're not here, but that we should think beyond just bioengineering for sure. At Technico, they have excellence distributed across many other disciplines. But yeah, the hard stuff now, it remains to be done. The most common diseases and even rare disease still don't have any cure. And so that's it. We know that it's time for engineers to take over, because I think we left the biologists do the bit, and now it's time to the serious stuff to be taken over by the technos like us.
Yeah, great note. Following up on this question for Professor Zita, do you think then applying for these European sponsorships, I guess funding opportunities, would be the one way to go for programs like HOPTEC to get even more established and like reach more people?
Yes, it's not just a question of money. Obviously, you need the funding to start the activities, but above all, you also need to visit, as it was mentioned here, you need to visit your partners. Yes, you can use Zoom, but it's never the same, as we know. You need to go to the place. You need to meet all the team, all the students. At the end of the day, we're just not talking about the top level. We're talking about the whole team. And to establish, you need the collaboration of everybody. And the funding, obviously. At this level, as I said, this is an Horizon Europe funding level. In Europe, we need that sort of funding and to bring all the teams and industry aboard. I mean, again, at the end of the day, you don't want just universities closed in a bubble. We need to talk with all the partners, including society, industry, etc. And as we were talking here, there was the time for medical doctors, there's the time for biologists, for engineers. We need to talk with everybody if we are to solve specific problems in our society.
Thank you.
I would like to say that it is now more and more common for, it took that long, for American groups to realize again that the expertise may be in Israel or in Portugal or France, and it's not bidirectional, but money can move from the NIH or the NSF or DOE, DOD to non-American labs. I wish Europe was also as welcoming of this exchange. That's okay, we'll forgo that. It was rich, I guess, but it's something that to me is the ultimate demonstration of a true partnership, is where you're copying a grant, you're co-authoring papers, and patent applications are happening both in Europe and the US at the same time. Now, these are milestones I hope HOPTEC will demonstrate, will achieve, but will be a great way to track of how we're doing the two institutions together.
Thank you.
Okay, I'll follow up to the next question. Professor Michael Baum, welcome. Professor Michael is associated with FLAD, the Foundation for Portuguese Luso Development in the US. And FLAD was one of the first sponsors of HOPTEC. And so following up on that, from your perspective at FLAD, how can international collaborations, namely with the US, be structured to ensure both cultural and academic impact?
Thanks so much. Wow, what a pleasure to sort of be here I wasn't here for the whole entire day, but at least from what I heard, very impressive, and we're super happy at FLAD to be supporting this kind of initiative between the two schools and the research that's going on. It's very impressive. So in terms of how to design, the cultural impact, my short answer is I don't think you have to. We at FLAD, we're generally focused on helping academic partnerships initiate. And at least in my experience, the cultural sort of spillover, if you will, you don't really have to design. I think when these teams come together and they start working together, these international collaborations, it's kind of like almost like the metaphor of soft power in the realm of international relations. The cultural goodwill. You're essentially sort of building these understandings, as part of the work together. I think it very much informed the spirit of the Fulbright, Senator William Fulbright, when he came up with the idea for the Fulbright scholarships. You build goodwill through actual international collaboration, and that's pretty much what we do at FLAD. Our mission is very geographically limited in terms of US, Portugal, but we support grants and opportunities in all kinds of different fields. And of course, I guess you could say the sort of built-in goal is sort of helping to create much stronger bonds between Portugal and the US.
Thank you so much. Going on the topic of expanding our program, and given that, for instance, two of you, Professor Wirtz and Professor Claudia, today you both talk about cell-based therapies. How can you see this program helping actual researchers, also to the point that Professor Wirtz was making earlier, to connect more closely and help each other, or really literally collaborate in projects that are using similar strategies but with different angles? How can we actually initiate that collaborative space and merge disciplines?
So what I think, and I'm glad that Professor Wirtz show all that impressive results of the CAR-T and the new constructs, and for sure I would be immediately thinking, when you do have those cells ready, let us help you to have a fancy protocol to speed up the multiplication of those cells and turn a manufacturing pipeline for their product. So definitely the connections are here. I think that we have to take these to the next level. So now we know that Técnico has great students. The students do great at Johns Hopkins, but most of the researchers still do not know each other. Mm-hmm. Now we know what Denise is doing. Denise knows some of the research that we are doing here, but probably now we have to organize ourselves, probably not go into too many directions, but probably identify 4 or 5 faculty areas in which the collaboration can be really viable and interesting for both sides, because in order to be interesting, it should be advantage for both sides, because as Inês was saying, we can always, all of us can benefit, because probably we are seeing we have the different angles of the research, and of course, Johns Hopkins is really a reference biomedical institution, and the cancer programs are really strong. But we also have these nice programs more on the manufacturing side, and this can be rather than for stem cells, and we saw today an example for a tissue engineering product, but the same type of tools can be used in this context. So I think that now is to promote initiatives in which we can have all-together events, either at Johns Hopkins, here at IST, in alternate years, for instance, and do all this work of networking to know what we are doing and identify the synergies and go after that. And then, of course, we already heard about the funding opportunities. Mm-hmm. Probably money that is from here, even from ERCs. We were talking that could be a co-PI from the US side, and also funding from NIH can also have the collaboration and the participation of European partners. So I think that the opportunities are there. So we have to do really now the homework of planning what would be the best strategy to go for it.
Sounds great.
The three of us, we can start this way. And I would almost say that just sheer size, right? Hopkins, I had to look that up, it's 3,600 faculty. So 3,600 research groups. Even clinicians are expected to do research, right? So it permeates all aspects of Hopkins. That we would start with your interest. And I could, in my position of VP for research, I do this every day, matchmaking, right? Matchmaking between your own interest and you could curate, what could be the strategic, first test bed way of engagement between the two universities, and then engage with the kind of mirroring groups to develop projects, right? We have, I have the means to seed some of this collaborative research. And simply the means also simply of a kind of, I'm going to use an old expression, Rolodex of all those people, and I can tell you, I don't work with this person, but work with this other person. there's that aspect too, that there's to be people who just are interested in not only just great, scientists and engineers. But I would say, let's get going, roll our sleeves, and thinking of in cosmology, in astrophysics, and many other disciplines, right? We likely to have fully world-class researchers of all fields. You went to the Goddard Center. There's a concentration in Maryland of all NASA-related industries you can possibly think of, but many other disciplines, right? And people think, medicine, they should. It's also public health, in a way. Physicians cure or help one patient at a time. They think of 1 million patients at a time. That's the way you want to think of public health. Another resource I'd like to highlight is the newly inaugurated Bloomberg Center. It's the Johns Hopkins Bloomberg Center. You're going to hear the name Bloomberg associated with almost every other initiative at Hopkins. Is an incredibly generous donor. The Bloomberg was the mayor of New York City. That Bloomberg. Bloomberg News is how he makes his money, and he is very generous, and he's help us take over what used to be the museum and transform it into academic space. And the idea is to turn Hopkins into a source of truthful information. In this day and age of misinformation and disinformation, maybe you suffer less from this in Portugal. There's a big problem in the US, to say the least. In a way, trying to capitalize on the success of the Hopkins COVID dashboard. Remember, during COVID, faculty launched this dashboard that became the source of information about patients, death, etc. And inspired by that success, to do this for many other disciplines, like people interested in not just virology or vaccinology, but interested in robotics or in AI, trust in AI. So long story short, can we use that space specifically for kind of US, European common kind of policies? We are 2 blocks from the Capitol Hill. We are making ourselves available to policymakers, and it's an asset that you ought to be thinking about, because unique in all of academia, right? All universities have a outpost in Washington, D.C. We more than just present there. We really have, I should have shown the picture, truly amazing in its location, but also in size. And that's something we should all leverage together. So another seed of something we could take advantage of. And that start placing Técnico also in a position of providing policymakers in Brussels about specific topics of technology. And more, you can't develop a technology in vacuum. You have to immediately think about how the public can support it. Eventually, it's their taxes that are used to support this research. And so I think it's time for us to recognize this a little bit more fully, and then make ourselves a lot more understandable to those people who are genuinely interested in understanding better what we do all day, in our labs.
The next question is for Professor Michael. So based on your experience from FLAD working with these transatlantic partnerships, from your experience, what would be or what steps can be taken to secure these long-term engagement between private and public sponsors, and what incentives might strengthen these commitments between these partnerships?
Well, I think by engagement, I'm going to assume you mean funding, right? and I'm here. I'm going to speak more, I guess, with my academic hat on, and less, as a member of FLAD. I think one of the things that one has to be, I don't know how many of you have heard of a woman named writer Jane Meyer. She's an investigative journalist, writes frequently for the New York Times. she had a great book that came out called Dark Money. And it was a real, I think, tour de force about, the way that private interests have really, sought to capture what they called the commanding heights and the ramparts of U.S. higher ed, and starting with the Koch brothers, for example. And, and I think it's a really instructive, kind of worrisome book about, as recipients, as a public university, thinking about where you're getting your private funding from. So I'd like to think that, our mission at FLAT is pretty straightforward. It's building bridges between the U.S. and Portugal, and, in terms of like what strings we might attach to our funding, we might say, well, to support your book, we'd love to have our logo on it, but we're not, really in the game of trying to direct, where the recipients go with their research. And I think, one of the things, especially in these fields related to cancer treatment and related to AI, we've got to be really careful about sources of private funding and what strings come attached with them. And I think, Bloomberg, I'm quite familiar with him, and he has a very, he's above board, and he's a philanthropist in the old school of, exactly, but there's what's happening at places like George Mason and the Mercatus Center and University of Chicago and in their economics field, and numerous schools in terms of management and law, and capture of those departments by certain private interests. I encourage you to read the book. It's an eye-opener. The short answer, I think for us is, at FLAD, we're really always trying to build programs that have a path to being self-sustaining. It's for us, that's really kind of the goal. Obviously, this grant was a very small grant in the world of grants, but I can already tell it's doing exactly what it was intended to do, generating even more fission, and it's going to lead to other important work between scholars and students working on different projects, and that's really our goal. So I guess my short answer is, pay attention to your funders. I was really happy to hear that you have a background in philosophy. So thinking about the ethics of what we're doing is I think, incredibly important. I oversee a new degree program at Catholic in politics, philosophy, and economics. So I was very intrigued by your background. I'm already being too long-winded, and everybody's freezing, so I'm going to stop there.
Thank you. I have one more question for Professora Zita. Given, as a student myself, and I think it is the real overall feedback that students at Técnico have, that, our content is very theoretical. We do have a lot of experimental classes and so on, but it's not the majority of the work we do here, right? We all know that. Do you think, a partnership with Hopkins, and this could be in many areas, given Hopkins' extensive research areas, do you think that could be a way to maybe try to close that gap? So imagine if all students could have the chance to do a summer internship in a lab there, and it could be mechanical engineering, space related engineering, things like that. Do you think that would be a way to overcome the gap?
So let me tell you something before answering directly to your question. I think that's fundamental. When we talk about partnerships, we talked a lot about research and academic exchange, but obviously we have to think about the students. That's why, and now with the head of Vice President, we're here for the students and for them to have mobility opportunities. I can tell you that we are part of the Time Association Network, which is a partnership with 50 different institutions from all over the world, which the main goal is to have joint programs and double degrees. And we have that mostly for Latin America, Europe, Asia, and North America. When I say North America, is Canada. One of the things also is that we'll take presidency next year, technical, because it's rotative. And I have to say it's the first time that they will have a female president, which for me was very surprising. So I'll be the president of that network next year, and it's the first time we'll have a female, which was very surprising, but we're happy that technical will give the example. Going back to those double degrees and joint programs, obviously we want to increase the numbers, and the Time Association Network is a very good example. But speaking of the US, we have double degrees with Western Michigan University. With Johns Hopkins, we don't. So we take this opportunity to actually try to start a conversation with Johns Hopkins. We have MOU, so there is already staff, academic staff and student exchange with Johns Hopkins. So that answers your question of let's have this opportunity. It's already in there, but obviously we want to increase the number of double degrees. So this is a great opportunity. And sessions like this one opens the door to actually start deeper conversations on that.
Yeah, thank you. I have one more question for Professor Ashley Kieman, and then maybe we can have like an overall discussion with the audience if anyone is up for it. But Ashley, in your opinion as a young faculty, would you see yourself, for instance, having interest in not only your students, but you yourself coming to Technic, for instance, or any other place in Europe for like 6 months or so? Because I think maybe faculty here, they would have that interest to go to the US. So, you know, could we do like an exchange faculty program?
Yeah, that's a nice idea. I do think going on sabbaticals is something a lot of faculty do, especially at the beginning. I think usually it would be, like Denis was saying, if you have a good match, you know, you make a good match with a team at Technico, they have a good match with someone at Hopkins, and the exchange has an explicit goal, maybe exchange of technologies, exchange of samples, but something that hopefully benefits both sides and has something that you can then take back with you and come back to the founding institution with some new ideas, some new methods. But yeah, absolutely. Sessions like this can help come up with some of those ideas.
Yeah, see where the needs are. Yeah. Thank you. Anyone from the panel wants to? Okay, there we go.
Denis wants to come to Technico.
Well, you could come teach a semester.
You asked me.
Wouldn't that be fun?
So it can be even a semi, I don't know if you want to call it a sabbatical for PhD students. Faculty matters, right? But often it's the students, right? You don't want to put me in the lab learning any technique. I'm useless, right? I barely graduated from Stanford, really. I don't know why they gave me a degree, really. But students, right? Sometimes there's a pointed technology. They want to learn about, you know, it's an algorithm that they think could have potentials. That can be a 2-month or 3-month stint, right? To learn about cell manufacturing, or you want to learn about these velocity receptors. I'd like to. Whatever and to learn and be on your way, right? There's then something in it for everybody, right? If even after a paper, right, you want that paper to be cited, to actually be used, right? That's the benefit to the person teaching a technology. We've seen this in this technology that actually developed called CODA, right? Where it is time now to kind of popularized its use. We were happy to be alone in Babylon, but now it was time to really get to the next level by making these algorithms, these pipelines available to a larger community. It takes then people to come and really learn the ins and outs, and it may be learn in 2 or 3 months, and then maybe focus on a common project to then, you know, start a collaboration, but having that student. So another version of HOPTEC could be for PhD students and postdocs here and Hopkins vice versa, to for short stint learn technology, be on the way. We have another technology on organoid modeling that's kind of taking off, and until you can read it 1,000 times from the page, and that's never gonna translate into really you knowing how to really use technology. And so I would like to propose to add to the basket of things we're thinking of shorter stints. They don't have to be 6 months.
I think, that is an excellent idea. You know, doctors do that all the time. They go like 3 months to an hospital to learn a surgical technique, and then they go back to their regular life with a new tool.
Right.
So we could really employ that in the engineering world.
Going to what Leonor was saying, expanding your network. It's a little bit of serendipity, but it's almost engineered serendipity, right? You learn, and then, yes, you thought you meant to learn a technique, and then you realize, no, it's the other technique that is now cooking, is in brewing in the lab. It's like when you go to the library. When we used to go to libraries, you thought you wanted to borrow this book, and it's the book right next to it that's the interesting one. It's the same, it's a version of this. You come with an intent, and it's okay if you don't fulfill that intent, you actually do something else. But now you have a network, right?
Yeah.
I just wanted to mention, especially for the students or young faculty in the audience, FLAD does have a set of grants that we call stagios for research in the United States for up to 4 months. They're on our website under Oportunidades, and you can essentially, as long as you have a letter of invitation from the institution in the States that you'd like to go to, you can receive, I think it's up to 1,400 or 1,500 euros a month, plus maybe some help for the flight. It's not a huge grant, but it helps. It's a helpful grant. And there's lots of other grant opportunities that we have on the FLAD website. That was just one that, as you were speaking, I thought is clearly sort of directed to what you were just speaking about.
American agencies are starting to realize that they need to help financially students who would come to learn a technique, as to really not just develop yet another technique and then dying on the vine because no one learns it, which happens all too often in academia. And so there are many types of grants that specifically support people staying on as well, that could complement this. If 1,400 euros is not quite enough, you now have an ability to complement that monies, which are very important, right? Because it's a validation, right? You earn the grant, and then you can talk to the NIH or NSF. Listen, this was highly selective. They got this grant. It's mutually beneficial, right, to have those worked out. Yeah, I agree.
Yeah, great point. Thank you for that highlight. I was actually going to say the same, because there are these FLAD grants that, they support exactly this, a short period of time. And also, probably the visa would be easier, right? Because only for 3 months. Yeah, the 90 days, yeah. Great. Thank you so much. And Andrea, do you want to add anything else?
I think that's all.
All good. Anyone from the audience wants to contribute? We have Leonor here. And then Professor Erlindo, okay? Afterwards. Oh, good.
Thank you for the...
No. There you go.
Thanks for the great discussion. Definitely some food for thought. And just picking up and maybe teasing up a little bit the discussion, we were talking about, let's say, bridging Técnico and Hopkins. We were talking about, let's say, the practical things about funding and about how do we bring people to one place and to the other place. And I guess I just want to sort of fast forward. I mean, I didn't imagine this day 10 years ago, right? So let's just, fast forward 10 years from now. And I guess the feeling that I'm having is, as an alumni of HOPTEC, if I can use the new brand name, right? As an alumni of HOPTEC, I'm not feeling I'm a Técnico student or a Hopkins student, right? I'm feeling part of something that crosses and unites. It's a new organism, if you will, right? As an engineer, and I guess one of the things that motivates me intrinsically the most is sort of the need for solving problems,
right? That we create that kind of platform where we could come together and find that actually we have common interests, common problems that we want to try to solve, and we are not sort of measuring, oh, I'm going to do that at Hopkins or that at Técnico. I'm going to do that at the best place where I can find the solution to solve the problem. Mm-hmm. And it wouldn't be just the two institutions, right? I think we can think broader in our networks, in our ecosystems, and thinking also not only academic institutions, but also in terms of industry. And I think, I mean, in industry, at least the practice of thinking of the problem to be solved is quite heavy, because you gotta really justify every single cent you want to put on research, discovery, and so on. And you really need to make sure that whatever you find out, you're gonna develop it and you're gonna put it in the market, because that's the only way you generate value back for the company. But I think beyond thinking about the industry's business model, I think for us it's really how do we bring ultimately value to the society? How do we really make sure that whatever we came up with is getting to the right place where it's going to generate that value? So my invitation is thinking 10 years ahead from this as a HOPTEC member, right? How are we going to leverage this platform? And then, you know, the money follows, because the idea is going to be great. I'm sure that someone is going to sponsor it eventually, but not that we just get caught up on the details, bureaucratic details. So that's my my invite.
Thank you. That was a great invite, huh? Now we have Professor Arlindo. Is that mic working?
Yes.
Okay.
So just one quick question. Actually, I have to leave shortly, but in my particular field, but I think in other fields also, master students are becoming more and more useful in research. Things that took 2 or 3 years and required a PhD work to do, I think now a good master student can actually do something very useful during a 12-month thesis or so. I don't know if this is also true in other fields, probably not, but the question is, of course, we are mostly centered on PhD students and postdoctoral students, but you feel this program also as is also instinct for actual good research being done by master students?
Oh, absolutely. I don't know if you were there attending Alfredo's and Inesh's presentations. So there are two types of master's programs. One where I'd love, in a way, the master's students to do something totally different. In a way, high risk, high payoff. Something maybe a postdoc would be hesitant to do, because or a PhD is hesitant to do, versus adding firepower to an existing project. So it's literally those two examples. Inesh, it was, you know, virgin territory mostly, and Alfredo, it was ongoing, but we needed now to start really analyzing all this data, and he did that. So it was, at Hopkins undergrads come with a mindset they're going to do research on day one. They don't wait to the masters. They're 17 and 18-year-olds, literally knocking on my door, day one, they want to do research. That's exactly why they came to Hopkins and not MIT or Stanford. This notion that you have to have this wall of knowledge to contribute your little brick to that wall is, to me, should be forgotten. I'm a huge believer in learning by induction. I come from the European system where the mindset was exactly this, right? You're going to only be able to contribute once you know everything that's been done before. But actually it's castrating. It creates a notion, a false impression, everything has been done, when actually nothing has been, in medicine in particular. And in a way, the naivete that younger people come is important. They don't know what they don't know, and it's beautiful.
They don't know what cannot be done.
Yeah, and therefore take gambles and chances that maybe again more seasoned and trained PhD and postdocs won't take. So I'm a huge believer in this. You'll come to my lab, you went to my lab, and you see this. There's 10 or 15 undergrads, and they can talk fluently about the research they're doing. It's not their little hooded hands and cleaning the wear. No, they actually, and at Hopkins, I mean, this is, I think admissions rates is like 5 or 6%. These are insanely, super selective and self-selected students, right, who are going to come because they want to do creative work, right? So long story short, I'm totally a believer in coming back in time in a way and not wait for people to, in a way, be set in their ways also.
Thank you both. Any other questions, comments, thoughts? Okay, let's clap.
Oh, one little thing. I hope for those students who are thinking ahead, right, that's maybe 7, 8, 9 months from now, we were talking with Claudia and I and Ines that we waited too long this season, this cycle, but think of now next cycle, when should it be? When students
we're probably going to do some sessions online, to share all the information, everything. Probably end of the semester, of the spring semester, so you can all prepare, or even earlier. Yeah, we're going to be advised by Professor Claudia here.
Yeah, she knows. But please, I know you're coming soon, but so that we can give you a chance to, kind of maybe plan ahead.
Yes, keep these options in mind. Okay, so let's give an applause to all our participants here. Thank you all for being here. Let's have our deserved coffee break. And then come back here just for the awards and the closing remarks. Thank you. Okay, thank you guys for staying until the end. We're going to announce the poster awards. Congratulations to all the presenters. Hopefully, next year you're all going to come back to Hopkins, right? Because it's going to be there. So we're going to announce, Andre, if you want to, we start with this one. And then when we call your name, please come to the stage and we're going to give you a certificate and we're going to take a picture. And then we're going to contact you so you can receive your 50 euros gift card. So for third place, Emaxi Naramato.
For second winner of today, okay, Diogo Engracia.
And then, last but not the least, first place, Caterina Franco Jones. Okay, and now let's just keep this going. For our Grand Competition Award, so this is an award that we are sponsoring in our program. We asked for proposals with one researcher from Técnico, one researcher from Hopkins. It could be PhD students and postdocs, you know. And it's a symbolic award, only 1,000 euros, but we hope this kicks off the collaboration between two people, you know, with a specific idea in mind. And so this year's winners are
Pedro Gonçalves and Frisco Du from Hopkins. And
Pedro, you can come to the stage. That's it. I take another. Oh, sorry. So Pedro and Frisco are going to be working on this proposal. Can the tumor targeting cell-penetrating peptide P28 hinder immune evasion in solid tumors? So we hope to hear back next year. Yes.
So we also want to, because it's the first symposium, we also want to address the HOPTEC scholars that won the last edition. Where is it? You have to go back all the slides. But Inez and Alfredo, if you could come here also as the awardees of last year. You also deserve a certificate.
We should say that these two students had a 19 out of 20 in their master's thesis, so another applause. Okay, so now closing remarks time. I think, we don't want to take too much of your time. We're just going to share some brief thoughts. We're deeply grateful that you all came here today. Grateful to all the professors who took some time today from their busy schedules. Particularly thankful to you, Professor Wirtz, who started all of this, and you keep investing in this. It's, your time, your money. So thank you. Also, big thanks to Professor Claudia, because she's been a real support here to, select the students and select proposals and so on. Margarida, we could not have pulled this event without you. Absolutely not. And, all the other people we highlighted before, Maria José, she's over there. Thank you. Also, thank you to Professor Ashley Keeman. You did a lot in our students' defense. Lots of hard questions, huh? But you did great. Lenore, thank you once again for being here today, because I know, you have a busy life too, and you spent the whole day here. Do you want to add any more things?
No, I just want to compliment what Ines said and say that the goal here is to really collaborate between these two institutions, and if you feel like you want to do a semester abroad or you have any lab that you're interested in going abroad, just send an email and we can try to help you. So.
Thank you to all the judges who graded our posters. Professor Nuno Bernardes. I don't know. Who was the other judge that you requested?
Dr. Rodrigues, she's no longer here. But
okay. And Lenore and Ashley. Thank you all. And now the big announcement of the day. We have selected the 2025 HOPTEC scholars who will be embarking their adventure in early 2025. We're going to call you to the stage, by the way.
Okay. So the 2025 HOPTEC scholars are Marco Costa and Catarina Oliveira. Please come to the stage. We took too long, so there's no more photos. Okay.
Okay. Oh, okay.
Okay, and without further ado, let's close this up. So feel free to have, we need a group picture, okay, group picture. So even though the group is a lot smaller now, but all please approach the stage. We're gonna take a picture, and then you are all invited to move to the cocktail Porto de Honra happy hour situation, which will happen here, right? Okay.
So everyone to the stage?
Yeah, let's, everyone on the stage. I mean, it's probably not gonna break.
Yeah.
Yeah, it's colder. It's colder than the building there. It's colder than.
Já tirarmos mesmo.
This is like cadaveric. My little doodoo.
Yeah, we can do a second row.
Yes, counterexample. Yes, let's do that. Stick around. You're not going anywhere. Margarita? Vasco, come here. Come here. Yeah, that's right.